So good day, everyone, wherever you are, in Asia, US, or in Europe. Welcome to the 4th International Crossing Conference in 2021, which from obvious reason is taking place in a virtual world. As we all now really much used to it, which is unfortunate because Crossing Conference is actually a very exciting conference, and we will come to that why. My name is Ahmad-Reza Sadeghi. I am leading the System Security Lab at TU Darmstadt, and I'm in charge of organizing this conference every 2 years in the last 8 years. It is on hot topics in security and privacy, and let me give you a very short introduction of what it's all about. And the next speaker will give you more details about, or let's say, a summary of different aspects of Crossing project and the Crossing conference that I'm going to talk about. So yeah, now my slide must work here. So the motivation is clear, I think, why you are here, and thank you for participating. Indeed, we are becoming highly dependent on digital technologies. If you look into the political agenda of many countries, they are all talking about digital technologies, and we have to change the culture and we have to go towards digital technologies, which is very interesting and very exciting, especially for scientists. And the emerging technologies like the trends from the last 10 years, so to say, there are still hot topics in these areas like Internet of Things. And very recently, artificial intelligence, covering a number of aspects and techniques and disciplines from graph theory into, let's say, automotive. Everybody is talking about AI. And these two emerging technologies that are also kind of connected to each other are really gold mines for security and privacy research, and of course the researchers who are working on these topics, because they provide in general no or very low security and privacy protection. So this is why it is important to dive into these emerging technologies and boost the research for security, because if they can have fatal consequences under the threats that we are facing today. And we don't know what threats we are facing in the future, we just have an imagination of it. So, and building trust in computing systems, of course, we cannot just bypass this ideology, it's indispensable. Now, Crossing project, a very, very short explanation of it, as I said, the next speaker will talk about it, is a collaborative research project of a big number of scientists, around 60 to 70, of German Science Foundation. These are usually prestigious projects because you don't get it so easily. You need a preparation of maybe 2 years to apply for it. And it is about security and privacy, or next generation security and privacy solutions. This is how I explain it to people who are not familiar with German collaborative research projects. So Crossing is multidisciplinary. What does it mean? It means that, as the name suggests, crossing, different disciplines cross each other: engineering, computer science, and physics. And the main idea is to generate new research paradigms, either in security, privacy, and safety, which are actually interconnected, as we know today, due to the growing or pervasive way of considering digital technology and how it is integrated slowly and surely in our societies. So there are a number of topics and areas that are considered in this project, and there are research results on that. from hardware and software security to quantum computing, but also cryptography itself, which is the core, one of the core topics of Crossing project, up to social media, because we know that security and privacy aspects are indeed concerning or kind of integral part of our daily life, even if we don't see it. And the goal is typically in every big research project is to have impact, either collaboration with industry and or publications at top conferences. And I think in these two, concerning these two aspects, Crossing was extremely successful, as one of the most successful projects I know in my academic life. And regarding the technology transfer, we have a number of startups, and I think this is an important topic, especially in Europe. Europe is that it's not so easy to set up a startup, but we have a number of just examples of that on blockchains, on quantum security, and on trusted systems that are very much connected to the research that has been done in Crossing. And why is that important? We will have a panel on that, because many of top people that are working in Crossing may decide to go to big enterprises, large IT enterprises. We know it's Google, Facebook, and others. On the other hand, it is also very important for universities that when young people are still very enthusiastic, they just try to make their own business, which we appreciate a lot, because then we don't lose these top people to big enterprises, because they have enough resources and enough funding to hire other people. So the goal of the Crossing conference, which is connected, of course, to the Crossing project, is what I would consider as the quote that I just a bit manipulated, altered it from what you have known from the movie Spider-Man. I think it's the global threat that we are observing today, we are witnessing today. There is a global, as comes to global responsibility. So one project like Crossing, and there are a number of other projects worldwide like Crossing that are important, that are delivering interesting results. It's not enough. It is the collaboration and it is the global responsibility, because we are facing global problems. If the supply chain is compromised, then you will see an attack somewhere in Asia, will have consequences in US or Europe because of the product supply chain. So this is a global responsibility, and for that we also need the global minds, the beautiful minds all over this world, to bring them together. And this is the idea of Crossing conference. It is not a conference where you send a contribution. It is an invitation-only conference, and if you have had the chance in the past to participate in physically, you know that it is not something that you can forget, because we really think 1 year about who is going to be invited, why this person is going to be invited, and how the society and how those participants benefit from the knowledge of these experts from different disciplines and from different fields of knowledge, and also from different ages, from different generations. So we also consider, so I personally really look into it, that we have a good combination of younger researchers with high potential, as you will see, and top-notch researchers that everybody knows. And I am very much blessed that nobody declined my invitation. So we are very happy that each 2 years we have so many top people that honor us with their views to these challenges of today. So we have a number of distinguished speakers, as I mentioned, in day 1 and day 2. So just to show the external speakers who are, as I said, from different generations, and some of them are you may know, some of them you may not know, but you will know them. Some of them are from academia, some of them are from research and government organizations who are doing really very interesting and impactful research. Some of them are younger researchers who are kind of rising stars, and we just put them together, and we hope that you enjoy the talks as far as time zones and time, your local time allows you. And some of these academia are also working very close with big companies on really challenging problems. And we are also very honored that Shafi Goldwasser from UC Berkeley and MIT accepted our invitation to give a talk. She's a Turing Award winner. Everybody who has touched the topic cryptography knows this name, and she has her work has influenced a generation of cryptographers. So in that sense, personally very happy that she accepted our invitation. So in day 2, we have other honored speakers, also from industry and from academia. But also organizations like DARPA, where Keith Rebello will give us some of his views to, for example, a fundamental aspect of security, which is hardware, because without hardware, you don't have any computing system. So, and to have also a view, a kind of overview of what are the pains and the gains of creating a startup, not only, especially in Europe and in Germany. It's, as you may know, it's not so easy, specifically if you want to do it in the field of security. We have invited a number of very experienced people who are either helping startups to get up. They have done that with many different startups, or they are kind of trying to provide the political strategy for it, like Ahmad-Reza, who is going to also be participating in this panel. And we also chose 3 very interesting startups who are going to explain and kind of elaborate on their experience of having startups. So before I end and give the stage to the next speaker, who is going to give you an overview of crossing, I would like to thank one person, and that is Johannes Buchmann, who was retired recently. He is the responsible person for everything that we have in cybersecurity in Darmstadt, which is meanwhile known worldwide. It's a very big center for security and privacy research. And the reason is that this person is not only a mentor and originator of Crossing project. I'm really missing him because he's now very busy in his retirement time, but even busier than before. But it is his vision of how to build together with top people something that it starts from nothing and then became an influential center for cybersecurity in not only in Germany and Europe, but worldwide. If you just count the number of top publications and the impact after US, there are several centers in Germany, but Johannes Buchmann was involved in this process of creating this environment, and specifically for Crossing. So I want to thank him. He is still with us. He's also participating, hopefully, today and tomorrow, and he's also advising us. But I really wanted to make this point that without him, there would not be crossing and there would not be a crossing conference. Okay, so that's some words, the last slide, some words to managing talks and Q&As. Speakers will be notified 5 minutes before the end of their talks. And please try to be in time. So I'm not currently in time, but I'm just opening. The attendees, our honorable attendees, can enter their questions into Q&A window that they can see on their screen, but also they can use the raise hand button to ask questions orally if they want to. And when they do that, we would like to ask our speakers or our attendees, when they raise a question, please introduce yourself and just say where you are from. I don't know, either you're a researcher or a student or working for a company, because we have a number of different guests. We have currently 200 registration. This is the number that we actually, around this number between 150 to 200 we want to have, and not more, because then even with 150 people, it's very hard to discuss topics. So last but not least, we are supported not only by German Science Foundation, but also by Huawei. Please, if you have time, visit the Open Lab for Sustainable Security and Safety. That is a joint project between TU Darmstadt and Huawei about making scientific achievements in system security open and working towards sustainable security. Enjoy the conference. And if you have any questions, any requests, if you need anything, just write an email or in chat. There is a contact information on web page of Crossing. And with that, I would pass to Marc Fischlin, who is the spokesman of Crossing Conference, the current spokesman or spokesperson, and he is going to give you an overview of the Crossing Conference. Thank you very much for attending. And as I said, please don't hesitate to ask anything about the conference and related topics. Thank you. So now I'm going to stop sharing and give it to Marc. Okay, Marc, stage is yours.
All right. Thank you, Ahmad. So also a warm welcome from my side. Good morning, good afternoon, good evening, depending on where you are in the world. I'm happy that we have the 4th edition of this Crossing Conference. First of all, let me thank Ahmad for organizing a great event again. We have a fantastic lineup of speakers. He already mentioned some names. I'll also tell you more about how the somewhat interesting title of this conference, contact tracing and quantum, actually fits into Crossing, and give you a little bit more insight about Crossing itself. So Crossing, Ahmad already mentioned this, is a so-called collaborative research center. These are prestigious funding instruments of the German Research Foundation, the DFG. And I know that there's a tendency to believe that the German language likes to form long words by pulling together individual words. And I can't deny this if I tell you that the German word for collaborative research center is Sonderforschungsbereich. So this is a single word and has a very highly distinctive meaning within the German research community. So Crossing itself is run by 3 universities, the TU Darmstadt, the universities in Duisburg-Essen, and the university in Paderborn. The reason is that it's 3 universities that we have colleagues who were at some point affiliated with TU Darmstadt and then got faculty positions at the other institutes. But luckily they stayed on board. This is specifically Eric Bodden and Luca Davi, and they still work with us on Crossing. So Crossing itself is mainly driven by 50 researchers on the doctoral and postdoctoral level. about half of them are funded through Crossing itself, and about half are affiliated and funded through other projects. And of course, there are also PIs. We have around 20, or in the second funding phase, it's 20 PIs. You see many of them on this picture here in the first two rows. For example, you can see Ahmad here in the, well, almost first row in the middle. And you see, for example, Sebastian Faust, who's the deputy spokesperson of Crossing. So in this picture, you see some of the researchers. You also see, I noticed that you see two members of our scientific advisory board, Farinas Kushanfar here in the front, and there's Reinhard Werner, a physicist. So they advise us in terms of how Crossing develops, and we regularly meet with them, and there is a meeting with them coming up in November, actually. So Ahmad already mentioned there's one person who is highly responsible that Crossing exists, and this is the gentleman here on the right. This is Johannes Buchmann, who started Crossing in 2014. Or actually, that's when Crossing started. I think the whole organization started 2 or 3 years earlier. And as I've said, the funding instrument by the German Research Foundation for such collaborative research centers, that the funding can go up to 12 years. And usually you have to file for a renewal every 4 years. And if you take a look, currently we are in the second funding phase of Crossing, and you see in 2022, actually in July, hopefully the third funding phase starts. And you can imagine this is 9 months from now, that currently we are busy writing the renewal proposal, which we have to submit at the end of the year. Now, part of this Crossing is the Crossing conference, which we organized and which Ahmad did for the fourth time, and he always does a great job of lining up interesting speakers. You see, it started 2015, 17, 19 was actually a full week of Crossing conference. There was a school attached to it and some industry event. This time we went for a virtual event for obvious reasons. And you can already mark, I hope, your calendar for 23 and 25 for the next editions of this conference. So what is the overall goal of Crossing? I usually don't like to put a lot of text on slides. Here I found that this is pretty much the most condensed description of what Crossing is. Let me guide you through the text. It says the idea is that we provide crypto-based solutions for the next and new computing environments. The solutions will be efficient, they will meet all the security requirements, and a very important aspect of our work is also they will have sound and secure implementations. And finally, one of the aspects which we also consider here in Crossing is they should be easy to use and be it for experts or non-experts, and they should be easy to integrate in other solutions. So this was the overall theme with which we started in 2014. It was the same theme in 2018, and it will be also our theme in 2022 for the renewal phase, just because we believe that this is still true. This holds. We need to have strong security guarantees, and we also need to be able to use them and have secure implementations of these. So let me briefly talk about the projects, and this will relate to, you can see why we chose the speakers and how they relate to the topics which we work on in Crossing. So here you see the 3 areas which we have. One is primitives on the lower left-hand side. This is about fundamental cryptographic primitives. Then we have the area solutions, which develops higher level protocols. And we have the area engineering, which deals mainly with the sound implementation of these primitives and solutions. So here are the projects. Don't worry, I will not go through all the details of the projects. The area primitive consists of 4 projects. One is about future public key encryption. And you see this is run by Johannes Buchmann, Christian Bischoff, Juliane Kremer. And this is, if I want to sum it up in a single word, this is about post-quantum secure cryptographic solutions. sanitizable crypto. That's myself and Sebastian Faust. This is about cryptography, which allows operations on the data. And you see, for example, we have this impressive keynote of Shafi Goldwasser about deniable encryption, which directly relates to the topics in these two projects. And then we have hardware entangled cryptography. This is Ahmad Sadeghi, and Stjepan Katzenbeißer is still a member in the second funding phase. He meanwhile left TU Darmstadt, but currently he's still in this project. And this is about the connection between hardware and crypto. And we have a wonderful lineup of people talking about this topic. For example, Jörn Müller-Quade will present his latest works on this. Lejla Batina, who I know is busy organizing the Eurocrypt conference end of this month. Nele Mentens. We have a keynote by Christoph Krügel. Ahmad mentioned Keith Rebello and Jason Funk, for example, will all relate to this topic. And of course, some of the talks range over several projects and topics we have here. So in the projects P1 and P2, there is some crypto involved, or post-quantum crypto, but the quantum aspect, which is also part of this conference here, this obvious in project P4 about quantum key hubs. This is a project by our colleagues from physics, Gernot Alba and Thomas Walter. And we have, I saw Johanna Sepúlveda in the audience, who will talk about quantum aspects. And then we have Gerd Leux from the Max Planck Institute. And I love the title of this institute. The institute is called The Science of Light. You see here is the quantum aspect. Now in the area solutions, we have attestation protocols. This is a project by Ahmad and Luca Davi. S3 is Michael Weidner, Haya Schulman about privacy preserving access. S4 is, I call it the channel project. That's Gernot Alba and me. S6 is a project which will unfortunately run out. This is about long-time secure archiving by Johannes Bucher and Stjepan Katzenbeißer. And S7 is the blockchain project by Sebastian Faust and Ahmad Sadeghi. E1, this is the engineering part. So project E1 is about secure integration, and I will mention a tool or a platform called CogniCrypt on the next slide. And for example, we have, and I saw his name in the list of the attendees, Liang Zhengkai talking about things about implementations and security. We have E3 secure refinement, Heiko Mantel and myself. E4 is the compiler for privacy preserving protocols, Thomas Schneider and Stjepan Katzenbeißer. E5 is about distributed computation, Mira Messini and Guido Salvaneschi. So I mentioned CogniCrypt. CogniCrypt is one of the important aspects of crossing. I'm not going to give you the link. I think if you Google it, you'll find it. This is really about a platform which touches upon the usage of the crypto, that people can actually use crypto in a secure and reliable way. And CogniCrypt was very much progressed in the first funding phase and went public in the second funding phase. So if you're interested in this, just go and check it out. So as I mentioned, we are close to the next funding phase or applying for the next funding phase. And in this third funding phase, the transfer will play a bigger role than in the first two phases. And this basically closes the circle. Contact tracing was a big topic also in the second funding phase. And I know Ahmad was very active in this area, and also Thomas Schneider, for example, and Crossing partly supported this. So as Ahmad has mentioned, we have an interesting panel about startups, and the transfer is also about applying or bringing the results of Crossing from the second funding phase to the third phase and working with partners from industry on these topics. And you see that there are some topics which are very prominent or will hopefully be very prominent in the third phase. One is artificial intelligence or machine learning, if you like. And we have plenty of talks about this. Srini Devadas, for example, has a keynote. Stjepan Picek, Salman Avastimer, Vahab Mirokni, Igor Linkov, Huda Hadari. So a lot of speakers in this area. Contact tracing, a keynote by Joel Reardon, and I know that Serge Vaudenay always has interesting things about to say about the security of such contact tracing protocols and apps. And blockchain may not be the most accurate description. Maybe it should rather say it's about smart contracts. And as I've mentioned, Amar Alcazar will give a presentation and run the panel. And he started as a colleague on the technical side. I mean, I think he nowadays works more on the political side. He's now Chief Information Officer, I think, of the state of the Saarland. So you see that the topic of the Crossing conference sounds a little bit strange in the first place, contact tracing quantum, but it all makes sense if you view it from our perspective, from the research we're doing in Crossing, and I'm very happy that all the speakers will share their thoughts, their insights, and the latest results about these topics and how they hopefully influence also our design of Crossing the third funding phase. So with this, I would like to thank you again, and as Ahmad said, I hope you enjoy the conference, even though it's not in person, but as a virtual event. Thank you.
So Johanna, Marc Fischlin already mentioned about the quantum aspects of or post-quantum aspects of our project. Johanna is a senior researcher at AIRBUS, the competitor of Boeing, and Airbus, I was told, is much better than Boeing. Johanna has done research in different areas, microelectronics, hardware, and she joined Airbus now for some years, and she's doing very interesting and exciting research there. She's also a member of European Council Advisory Board for quantum or industry-related quantum technologies and quantum security. And I'm very pleased that she accepted our invitation to give her view of, let's say, quantum technologies. And the talk is called Demystifying Quantum Technologies. Johanna, the stage is yours.
Thank you so much. I will start. Can you see my screen?
Yes.
Okay, good.
Just need to go to that. Exactly.
Okay, good. So thank you so much for the invitation. In this talk, I want to address the different opportunities and challenges of the quantum technologies. And I also want to make a call for all the security community and why this kind of technology can be also like a point of interest in the sense that has some opportunities, but also we have to further help to increase the security in these technologies. Okay, so let's start by discussing the quantum principles. So currently there are two phenomena that rules all the quantum mechanics, the two quantum mechanics phenomena that rules these quantum principles, and they are the superposition and the entanglement. The first one, the superposition, says or dictates that all states are possible simultaneously. But these states collapse when somebody observes or measures it. So when we observe these states, we are collapsing to a single state. The second principle is the entanglement, and it dictates that the entangled particles are, or particles, quantum particles, are it's all that physics that are related to the physics with the very small particles. It says that these particles are somehow connected or can be somehow connected, and that is called that they are somehow entangled. In an entangled part or measure of the state of a particle, we influence the state of the second particle. In addition, these kind of quantum mechanics can be used to encode information, and we can encode information as in a way of qubits or quantum bits. So this is a fundamental carrier of quantum information and can be geometrically described like an sphere, when we have different poles. The pole of the north is the 0, the one of the south is the 1, and the state is are encountered in all the surface of this sphere. Whenever whenever we observe this qubit, the state will collapse to a 0 or to a 1 in this qubit. In addition, and just this is the last part of the quantum mechanics part, is more about the measuring. So I mentioned the sphere that can encode a 0, 1, and all the possibilities that are in the surface of this sphere. These points in the surface are described mathematically like a complex vector. When we measure it, we have seen here in the slide, for example, a superposition between a 0 and 1. So it is, I state that this is between 0 and 1. But here we saw that we have a dominant state, that is the 0, because the point is more close to the pole north, that is the 0, 1. So when we measure these qubits, we will have some probabilities of that the outcome will be 0 with high probability, and we have also some chances that this measure will collapse to 1 with lower probability. So here we have to mention that we are talking about probabilities, so different shots or execution of this measure are required. We can use different kind of technologies to fabricate this kind of qubits. Each one of these qubits, we have to take into account that according to the technology, they can be more or less stable. So we can imagine this qubit like some balloons that with the time we lose the shape, and then it is difficult to compute with them. So what can we do with them? So they're very exciting because we can explore different kind of states due to the superposition and entanglement of the particles. We can also process and encode information in a different way. So that is why we can currently we are hearing everybody that there is a high development and a high rate for the quantum computers. In addition, all these quantum phenomena can also be used for security, for security purposes. Once that nobody can observe this qubit without modifying the state of these particles. So that means that it has a very huge eavesdrop capability, what is of high interest for very highly secure applications. And the third application is sensing. So by using entanglement mostly, and a part of superposition, we are able to see the world in a different way. So here we are going to very quickly look at these technologies. And one of the motivation is not only because it is a new ways of processing, sensing, and communicate information, but also there are envisioned that quantum technologies will be a very huge source of revenues for different markets. And in addition, many countries are highly investing in such a technology. So here in the graph, we can observe the quantum technology funding for the EU in the different countries. This is a survey for 2019. And just highlighting that, for example, some of the budget for Germany is up to 3.5 billion in order to develop computing, communication, and sensing capabilities. So with this in mind, so let's start by what is quantum computing. So quantum computing and what is at stake with this? It's a new way of process and encode information that allows to have a higher parallelization, explore different alternatives in a reduced amount of time. So this is very interesting for mainly three applications. The first one is simulation and modeling of complex systems. So by using quantum computers, we are able to explore and develop different multi-optimization kind of applications. So with that, different kind of molecules are now being simulated. A complex system can be further explored and designed. So the second application is optimization. So with these computers, we can also converge or search in a more efficient way, which is the optimal path. For example, in a trajectory, we can also further go to the optimized multi-objectives design, and this is the second application. And the third one, that is about the security. And that is what is a threat, these quantum computers. So with these quantum computers, they are able to execute the algorithms of Grover and Shor. And these algorithms are able to solve in polynomial time the hard mathematical problems on which the current cryptography is based on. So that means that they also represent a threat for security. So in these quantum computers, we basically operate the qubits towards or through three kind of operations. The first is rotations of these kind of states of the qubits. The second is the interaction among other qubits. So we are able to entangle particles and then enhance furthermore the power of this search. And the third one is the measure of these qubits. A circuit in a quantum computer of general purpose will look like this. So here we can see that in order to decompose or to create a bigger rotation, we can decompose this into the different steps. So the steps, so very similar to what happens now with the digital circuits. We have a set of inputs and outputs when each line represents the process of transformation of a single qubit. When we have each one of these boxes represent gates that perform some kind of transformation of the qubit. And we can see that some of these gates are able to transform or to operate two different qubits in somehow entangled their state. Here in the figure, we show circuit with three wide. So that means that it is operating three different qubits and a depth of 7. So that means that we have 7 steps that operate. The current technologies have some limitation in the implementation of this kind of circuit. So as I mentioned before, the qubits lose the shape or lose the state with time. So that means that they have the coherence that it relates with the interaction among the different qubits. So the interaction among them is limited. Also, we have the kind of number of steps that we can perform with it. So that means that in the future, one of the challenges to implement different problems, it is to have better circuits. Currently, we have to limit the design of the circuit to very short and very mostly very short circuits. So the less operation, the better. Currently, I'm just for finishing this part of the quantum computing. The quantum computers are just good for performing some specific tasks. So the general purpose computers are not going to be replaced by quantum computers, but these quantum computers are going to be a specific processor that it will be used for very specific tasks. Currently, there is a huge development for compilers and also libraries of circuits that can be used and tested in an open environment. And also there are some companies that are offering this quantum as a services. Different kind of technology and different chips have been presented to the market. Here in the slide, we can see one of them. Some of them has claimed already quantum supremacy. So what is quantum supremacy? Quantum supremacy is obtained when a quantum computer is able to develop a task several times faster than the most faster supercomputer. And that already has achieved for the first time in 2019 by Google with the processor Sycamore. And recently, two other quantum supremacies have been claimed in China by the computers of Yuisang, that it was based on optics, and other new chip that is also based on semiconductor technology, such as the one of Google or IBM. Good. So quantum computer is a new computational paradigm only used for a set of problems in the part of security. It also may help us for cryptanalysis, for example, exploring different kind of security vulnerabilities of different systems if we achieve to model this system in a quantum way. In the second technology, I'm going to talk about quantum sensing. So quantum sensing is one of the most oldest application of quantum and has been deployed in medicine, transportation, avionics, etc. So currently there are different kind of technologies, as you can observe, as this is like the less important technology here in the part of security. I will be a little bit more faster here. But what I can see, I want to say is that there are some technologies where they have big applications and impact in the different business and markets. So not only in the health sector, as I mentioned before, but also in the part of navigation, surveillance, detection, and sensing. In the part of sensing, these Rydberg atom sensors can be of interest for the security community. Ones that they are very sensitive to, they look like they are able to, they act as antennas, and they have the potential to be powerful tools for performing different side channel attacks in different systems. So this is something that different groups are currently looking at. Now let's go to the part of communication. So as I mentioned before, we are the quantum computers also, they are not only good for all what I have mentioned before, but they also represent a threat for the current cryptography, since they are able to solve in polynomial time all these hard mathematical problems on which cryptography are based on. So to better understand what does it mean, it means that currently our security is considered unbreakable because it requires a huge computational effort to solve these problems. So it is expected that, or is estimated that with the best attack, with a classical algorithm that is executed in a classical computer, that it has the potential of operation of 1 trillion of operation per second, it is estimated that it requires 17 trillions of years to solve these problems. However, in the quantum computers, we have another reality. There are some quantum algorithms that were designed to develop a specific search and also the quantum Fourier transformation. And this kind of operation has an impact on these algorithms. The first algorithm, it was invented by Grover. The Grover algorithm is a search is a search algorithm, a quantum search algorithm. And by using this algorithm, it is able to halve the security of the current standards, one of the standard symmetric cryptography. So that means that it will reduce half the security of the AES. So in the future, when these quantum computers can execute these powerful algorithms, it should be used the AES 256 to keep 128 bits of security. The second algorithm, it is the Chor algorithm, and this algorithm is very powerful because it can solve the public key cryptography. It's very good for the factorization long or big primes, and that is why it's expected that when a powerful quantum computer, it will break the public key cryptography in around 10 seconds. So that's why new alternative, new secure communication should be researched or should be put in place when this threat comes. So there are two different kind of solutions. The first one is the post-quantum cryptography, and the second one is the quantum key distribution. So, but how long or how big this computer should be in order to really represent that threat? So in order to understand here this, I want here to present a summary about the evolution of the development of the quantum computer in the latest years. One thing that we can observe is the exponential evolution of this technology, also the increase of the amount of qubits, and there's another aspect to highlight here is the kind of technologies that are used now for building these quantum computers. I mentioned already some like the superconductors, that is like IBM, Google, etc. But also they have ion trap, spin, and neutral atoms as very promising technologies for building these quantum computers. Currently, we have a record of qubits of 65 qubits by Sycamore. And in order to break the current public key cryptography, will be required at least 1,000 operational qubits. And I want to highlight this, it's operational qubits, so that means that are the stable qubits, are not physical qubits, but the stable qubits. In addition, the first one that, or the first cryptographic primitive that will be, I have a sound, okay, will be broken will be the elliptic curves. So let's talk very fast about what is post-quantum cryptography. So post-quantum cryptography, you should know about that. There are different kind of algorithms that are based on hard mathematical problems that are very difficult from those or which we currently use. And by enhancing this our communication channel with this kind of algorithms, we can create post-quantum or secure channels that are resistant to traditional attacks and to quantum computer attacks. With these kind of algorithms, we can encrypt, decrypt, sign, and verify. So we can perform a wide variety of cryptographic operations. In addition, I want to highlight that these kind of algorithms can be already deployed with our current technology. So they are just algorithms that are resistant to these threats. Currently, we have 5 different families, and each one have different advantages and disadvantages. The first one is the code-based cryptography. This code-based cryptography is based on mathematical problems that are very well studied, and they are multi-purpose. So that means that they can encrypt, decrypt the information, but also sign verify. However, the most popular is for using for encrypt and decrypt information. And these are also very fast. However, what is the con is that they have very large public key sizes, and that will limit their applicability in some of the applications. The second one is the hash-based cryptography. And in the hash-based cryptography, we also these algorithms of this kind of family also relies in hash on the hash technology that is very well known and very well studied. It's very efficient. However, it doesn't have any encryption scheme, so that means it's only used for signature and verification. And in addition, in the implementation, sometimes it requires, and some of these require the track of the signet messages and use keys. So it requires a little bit more effort in the implementation. The third family is the multivariate. So the multivariate has also are multi-purpose. These so that means they can encrypt, decrypt, and verify, and also they are very efficient for signature schemes. However, their basis of the security have been severely attacked and impacted with different kind of attacks, and most of them achieve only very low levels of security. The third one are isogenies, and the isogenies has they are based on elliptic curves, and a very special construction of elliptic curves. So the advantage is that we have worked with the elliptic curves, we know them, so it is very familiar to us. However, and also they have the smallest key sizes, which is very attractive for many applications. However, it have a very low efficiency and also are difficult to construct. The fourth family and the five family and the last is the lattice-based cryptography. Currently, has been proven to be very efficient and also very rich. So that means that we can not only encrypt, decrypt, and verify, but also we can construct more complex security primitives like FHE and IBE. However, the key sizes are still larger when compared to the traditional cryptography. So as you see here, we have a wide variety of selections, and there is not with different advantages and disadvantages. So currently, this post-quantum has been under the develop or under the scope of different standardization efforts. And here I highlight the needs that is driving this effort in selecting the algorithms to be standardized as the post-quantum standard. It was promises that until the end of this year, the candidates that will be standardized will be announced. However, this was not only topic of news. There already have been several discussions and also some standardization in other bodies. So ANSI already was discussing these topics. IEEE has the standard 1363.1 in 2009 when they standardized some lattice-based cryptographic algorithms. ISO as well is discussing and has a group dedicated for this topic, as well as ETSI, where ETSI is focusing on the developing of white papers, education, etc. In addition, we have other communities like IETF, and especially their research part that is they call IRTF in the group of Crypto Forum Research Group, where they are in charge of developing the next generation of standards. So how do they work? They receive some internet draft. When they receive a raw description available to everybody, it has been discussed in the committee, and then at the end, a request for comment on document or RFC document is generated, and this will become later on de facto internet standard. So just notice that this body is in charge of specify, and currently they already have published 2 RFCs with regards of post-quantum cryptography, and that is the RFC 8391 in 2018 and the RFC 8554 in 2019. All are some hash-based post-quantum primitives. After this, and with the advance of the standardization of needs, IETF has received a huge amount of internet rush with raw description with the different proposals of post-quantum primitives and how to integrate to the protocol. However, IETF has decided to stop these kind of discussions and wait until NIST just decide which are the primitives to be used, and then they will start to discuss how these primitives will fit to the next generation protocols of security in internet. In addition, there are different security bodies, and not only NSA, but the NSAs of all around the world. And here I also highlight the one of Germany. Each one are investing in further researching about this topic, and they have published different recommendations about the use of the post-quantum cryptography for the early adopters users. So, and as a very fast summary of the NIST, the standardization body. In regards to with the post-quantum cryptography, so it was developed in a round-basis approach. Currently, we are in the third round. So in the first round, as you see in the table, we have the number of candidates per family. So where lattice-based and code-based were some of the families that has many candidates or algorithms that were claiming these post-quantum properties. In the second list, the second round, it was further reduced, and now we are in the third round of NIST finalists that was announced last year in July. And the different algorithms were divided in two categories. The first category is the finalist, where the finalist it includes the algorithms that where some of them will be selected until the end of this year to be as the standard of post-quantum. The second is the alternate, that are some algorithms that are interesting, but they are not ready yet, and they should be further evaluated, and they let them so that everybody can further study and contribute to them, and maybe in the future, maybe they can be standardized. Here's some of the zoom in to the different finalists. So we have from code base, we have a KEM of Mac-Elise with large key sizes, of course. We have Lattice, and we have Kyber, Saber, and Entru. And for signatures, we have the multivariate Rainbow, which was in February, it was their security was impacted, and the security was reduced. And the last one is the Lithium and Falcon, two signatures that are lattice-based. So what is the problem? We have already solutions in place. So here is some of the benchmarks of the post-quantum cryptography with ARM processors. And we can observe the different characteristics in terms of key sizes and performance for the key for the KEMs and for the signatures. And what we can here with the red start is the location of the traditional cryptography like RSA or elliptic curves. So what we can observe is that while some of the algorithms can be faster than the traditional cryptography, for the key sizes it's always worse. So what does it mean? So that means that there is not an obvious best post-quantum alternative. It will depend or be driven by the use cases. And the second is that the post-quantum plug and play is very unlikely. It's going to be require some additional effort toward the integration of these algorithms into the different applications and protocols. And the third one is that we might not meet the performance requirements, since we have, it is not only that the primitive itself is fast enough, but how we can communicate between the parties. And as we have longer key sizes, and maybe for unreliable communication systems, then we will have a problem there. There have been different experiments regarding the integration post-quantum into real-life application or into some test application. Some of them have been developed by Google 2016 and 2019, where they enhance the TLS by including post-quantum primitives. Also, recently, Microsoft also investing a huge effort on profiling and developing these kind of studies. So here in this kind of protocol, how does it work? The Google experiment. So they have as a traditional cryptography the X25I19, that is an elliptic curve Diffie-Hellman, which provide 100 bits of security. So they make an hybrid approach, wide hybrid. So the idea is that we have a traditional layer and over a quantum, a post-quantum layer, so that in case a post-quantum layer it is broken, at least we have some of the traditional baseline. So here the client will support both, not only the traditional cryptography, but also the post-quantum, and they are going to create some ephemeral keys. Then some shared secrets will be generated and transferred, as it shows here in the protocol. And at the end, the master, they can agree in a master secret by concatenated the two shared secrets, one that is function of a traditional cryptography and the second that is function of the post-quantum cryptography. And now let's go to the quantum world. So as I mentioned before, post-quantum cryptography algorithms that you can implement into traditional technology to achieve a protection against quantum computers. So now let's talk about the quantum key distribution. So the quantum key distribution, the goal is to use a quantum channel to transfer a secret random key. As I mentioned in the beginning, the advantage of this kind of technology is that it's impossible that an attacker can eavesdrop the channel without being noticed. And this is very important for highly critical applications. So how does it work? We need a classical network. Then one of the parties will create a random a key. This key will be encoded into through a quantum device, communicate to a quantum channel until the next party, which can be like retrieve and convert to a digital key, and then both can communicate using, for example, asymmetric cryptography like OTP or AES. Yeah? So that is how the main goal of this kind of technology. Of course, it has some disadvantages, like it requires previously authenticated channel. So the main protocol was invented already in 1984 by Charles Bennett and Gilles Bazard, and here I'm going to explain how this kind of exchange will work. So as I mentioned before, we have two different channels, a public and a quantum channel. In addition, Alice has some encode bases, have two encode bases, one that is horizontal or vertical or live or red. So she can encode her bits into quantum information through these bases. In the other side, Bob has a measure basis where he can measure the information according to these bases. When the bases and the encoding are aligned, then he can retrieve the information. Otherwise, he will get a perfect superposition and he will get an error or a random bit. So how it works, it is defining in three different steps. The first one is encode. So Alice will encode the bit and will select one of the bases randomly and encode her into the quantum information. So here, please notice that the one can be encoded as a vertical or as a right qubit. These will be selected randomly. Then Bob will also select randomly some of the measure bases and will receive this kind of photons. Of course, we know that when it is not aligned, like in this case, it will receive an error. When it's aligned, it will receive the qubit. And this is in the measure step. And the third step is reconciliation. So after this measurement takes place, the two parties can agree in which were the bases that they were using, and they can perform a key distillation, a sifted, from the sifted key, they can further perform a key distillation when they can select some of the bits that they can get rid of, and the other will be the secret key. One thing that you notice is the loss of the low throughput of the key. While we send 8 bits at the end, we get just 2, and that is somehow the ratio that we have today with the current quantum communication technologies. In addition, there is the previous was the first way of communicating information, that is the prepare and measure type. The second type is the entanglement, when a high energy photon is divided into 2 low energy photons. These 2 low energy photons can be later distributed to, they are entangled because they belong to the first energy photon. So these entangled photons can be later distributed to Alice and Bob, and then Alice, we create like an entangled channel. And Alice, by interacting with this entangled photon, can transmit, they can modify the quantum state and can transmit the information to Bob. So we have something like that, and that is how the satellite will, it is mostly used in satellite.
Just a second. 5 minutes left.
Yes, yes, thank you. This is the kind of preparation that it used, and it already was put in place into satellites. So here it was the experiment that I was showing missions in the satellite missions in 2017, where they are able to perform or to deliver this kind of quantum information to different places in China. Here are some of the different experiments with QKD that have been developed in Germany and other parts of the world. I want to highlight that the LEO orbit, so in the space we have different layers of constellations or areas, and the LEO, that is the low Earth orbit, is one of the most used for QKD. However, you have to notice that for implementing this QKD, we don't only need the space, but also the terrestrial part. So I will skip this. Or no, so what are the current drawbacks of this technology? So we currently have to use the space and the terrestrial in order that we can further achieve a long range of communication. Currently, the optical fiber only is able to cover short ranges, so that is varies from 20 to 100 kilometers. If we want medium range, we have to use different trusted nodes, and for longer ones, we have to use satellites. So the trusted nodes are just like a repeaters, or that has they consist of a quantum receiver and transmitter that is hosted in a secure boundary to prevent tampering. And this is basically one of the weakest point of the QKD, because it's where the quantum technology will become classical again. They have to make a transition between the classical to quantum to classical, and this is a point of concern. So this is, it is mandatory that these points are built in against tampering, but it is not only tampering that is that it can target these systems, but also the passive attacks. And then it includes all that we know about the different side channel attacks. Trojan also is a big concern in this technology, and together with fault injection. So to further secure these elements is mandatory. In addition, with the development of these quantum sensing or sensors, also that becomes another target of a threat for this quantum communication. There has been several demonstrations since 2002 in DARPA, continuing by 2008 in Europe, Tokyo 2019, Italy in 2018, and the recent Cambridge 2019. However, this is some of the most advanced demonstration is in China, where they are able to span in 2,000 kilometers, and they can also further go to 40,600 kilometers by QKD links. And this is something that currently different countries are looking towards developing their own quantum network. As I mentioned before, so we have this problem of communication. We have different, this is my last slide. So we have the post-quantum cryptography, key distribution, all are, they have different advantages and disadvantages. And in the future, it's foreseen that these two technologies will work together. So it's not that our competitor technologies, but they will have to work together in order to make a quantum secure communication. So to adopt quantum is a different mindset, it's challenging, but this is very promising. It is and it may be a game changer. So thank you so much. And
with that, I would just like to go to our next honorable speaker, and that is Jörn Müller-Quade from Karlsruhe. Jörn is the professor and head of research in a kind of excellence cluster, as we call it, for cryptography and security in Karlsruhe. He's one of the, so to say, pioneers in bringing together theory in security and computation. And practice together. So, and this is why his talk is also about how you can use hardware trust anchors for in the context of secure computation, and which is also one of the major topics in crossing, but also in worldwide research in cryptography. And I am really happy. I was a bit concerned that Jörn, because he's a busy man, he may not be able to come to our conference, but he accepted my invitation, and I'm really happy that he's here. Jörn, you are the great man for the stage, please.
Thanks a lot. Am I supposed to share my screen myself?
Yes.
Yes.
You can.
Then I will. Okay, can you see
yes,
my
you just
screen?
need to go to presentation mode.
Yeah, I will.
Great.
Okay. Thanks a lot for inviting me. And I would like to talk about how secure hardware can improve secure multi-party computation. And and first, because maybe we do not all remember what it is, a secure multi-party computation is not only about a key exchange or digital signatures, but it is a more complex cryptographic algorithm protocol where a group of mutually distrustful parties wants to evaluate a function on their private inputs. Examples would be auctions where the private inputs are the bids, and the output of the secure computation should be who's the winner and maybe the highest bid. Private intersection of data sets is a very well-known example, because you could have like lists, and you would like to know, are there any entries on both lists? So the private input would be a data set from Alice and a data set from Bob, and the output would be the intersection of the two sets. Also, electronic elections can be seen as secure multi-party computations, even though there are some additional problems about coercion, which I will be not talking about today. But you can imagine that here the private inputs are the votes and the result of the secure computation is the tally. And now, will secure hardware make all multi-party computations trivial? I claim that secure hardware has not been in the focus of MPC research because it was thought to give kind of an unfair advantage and would make MPC very uninteresting, trivial. However, in this talk, I will give two maybe not so well-known examples for a non-trivial use of secure hardware in MPC. The first will be, in a certain connection to the previous talk, everlasting security from signature cards and a quantum channel. And the second example will be protecting the parties in the MPC, in the multi-party computation, from being hacked, from remote attacks. So I would like to make the security model, the threat model, a little bit more realistic, because hacks happen. Okay, a secure multi-party computation is a protocol. You pass around messages, and the parties, in this example, P1 and P2, mistrust each other, and they would like to, with this protocol, achieve a joint computation on their private inputs. I will import a result, a famous result, that every protocol task can be implemented even with unconditional security, meaning not relying on computational assumptions, given oblivious transfer. I will use this result in a second. Okay, I will switch to bit commitment for a short moment. This is a protocol where you kind of fix a bit without revealing it. And later on, you can unveil and prove that this is the bit you did fix some time ago. Okay, if we want composable protocols, then Canetti and Fischlin proved that you need a trusted setup. The reason is that you need to be able to extract what is committed as the sender. So kind of the sender must know the bit he or she commits to. And this knowing the bit is only possible with a trusted setup. And this trusted setup could be kind of a public key, which is known to everybody, but no one knows the secret key. Then in a simulation-based security model, this trusted public key could be chosen in a way that the simulator knows the secret key and can, for example, extract. However, there's a different way to extract. We can use trusted signature cards to implement UC commitments. The idea is the following. If you sign a message with a signature card, you have to give it to the signature card in the clear. So you can only sign messages you know. And now we will use this as a trick to build a commitment where we know what's inside because we have signed it before. So to achieve this, we sign the message M. Now, in the list of all messages we have signed so far, there will be the message M, so we know M. And we will sign randomness R, and then commit as follows. First, we will commit to the message M and its signature using the randomness R, and we use a second commitment, committing to R, the signature on R, using some randomness S. And now I can extract, because I have, if this is a valid commitment, I have on the list of what was signed before, I have M and I have R. So I can compute possible commitments and just compare and find the suitable M and R for the first one. And then I know that M can be the only message being inside here. And I don't need to extract from the second commitment, because if this is not well formed, I will be unable to unveil, and then simulation and proof of security is kind of easy. I'm not interested in the case where I cannot unveil, but I'm very interested in extracting M. Now, if we can extract M, we can build these UC secure commitments, and we can extract M if we use a trusted signature card in the way I showed. Actually, Katz found out something very interesting in 2007, that you don't need really trusted devices. Tamper-proof devices are enough. You need to just trust that the other party cannot break it. So I will build a signature card on my own, and I will hand it to Bob. And then I'm sure that Bob cannot break it because it's tamper-proof, but Bob will not necessarily think that it is a trusted device because it comes from me. So following the idea of Katz, actually, we can improve the result further to use untrusted but tamper-proof signature cards. So now we know that with signature cards, we can build extractable commitments. This extraction and the equivocation, I didn't talk about that, also works if the commitment is unconditionally hiding, meaning information theoretically hiding. And thus, we get everlasting security for commitments and, for example, zero knowledge as an application of commitments. Why everlasting security? Everlasting security because if you don't break the signature scheme while the protocol is running, then you will only be able to build well-formed commitments. And if these commitments are not unveiled, they will be unconditionally hiding, and so they will not be broken any time in the future. And it was proven that this is impossible without hardware assumptions. So everlasting security for bit commitments and extractability composition is not possible without hardware assumptions. Now, we can even come from bit commitment to oblivious transfer to arbitrary multi-party computations. From OT to arbitrary multi-party computations, I mentioned that there is a famous result by Kilian, and there are many more variants, more efficient variants to get from OT to MPC. But how could I come from bit commitment to oblivious transfer? If we were given a quantum channel, okay, then we could send a qubit, as mentioned in the previous talk, as in such a BB84 scheme, in one of two possible bases, and the receiver, Bob, would measure in one of the two possible bases at random. And now, whenever Bob chooses the wrong basis, the information is lost. However, Alice cannot know if the information is lost or not. And so we have oblivious transfer, we have an erasure channel, a provable erasure channel, and from this we can build oblivious transfer. But there's one problem. Bob can just refuse to measure because later on, Alice and Bob will have to compare bases to know which bits, to have Bob know which bits are real bits and which bits are lost. They have to compare bases. But if Bob just measures later, after having received the information about the bases, Bob could measure all photons in the right basis, and this would not be a secure oblivious transfer because Bob would know too much. There would be no erasures. And for that reason, the protocol proposed by Crépeau is that we force Bob to measure. We force Bob to measure by making him commit to which basis he used and making him commit to which result he got. And later on, we will test some to see if Bob really measured often enough to pass the test. And then he measured often enough to have really destroyed information. And we have an erasure channel. And on top of the result of the everlasting commitments, Unruh proved that you can get, with this Crépeau trick, everlasting oblivious transfer. And from everlasting oblivious transfer, using the classical results, we get everlasting secure multi-party computations for all tasks. And I think this is a great promise because we will have progress in the future. But we can fairly well know maybe the technology right now. So we have to only look at this protocol not being broken now, and it will become everlastingly secure afterwards, and it will not be broken in the future. And it's impossible without secure hardware, without these everlasting bit commitments for which we did use the signature cards. Okay, secure multi-party computations. Recall that a group of mutually distrustful parties wants to evaluate a function on their private inputs. But what is often neglected is that even if I'm honest, my computer could be hacked. I might not know that someone is able to control my computer remotely. So I would like to enrich the threat model for multi-party computations with the case that there are honest parties, but their computer is remotely hacked and not under their control anymore. And we will try to obtain secure multi-party computations in this case, and we will be using secure hardware, and it is impossible without. So classically in MPC, there are two corruption models. Either the set of corrupted parties is fixed prior to the start of the protocol execution, meaning protocol participants conspire before the start of the protocol execution, or we have adaptive corruption, meaning parties could become corrupted at any point of time during the protocol execution. The intuition behind such adaptive attacks is a remote attack, that someone hacks you while you are running the protocol. However, up to now, all MPC protocols leak the private inputs of the parties which are hacked, meaning they claim that it's maybe kind of impossible, and without trusted hardware, it is impossible, to keep the inputs private of those parties which are hacked. So all adaptively secure protocols so far have the property that by a remote attack, while the protocol is running, you will obtain the private input of a party, even if this party is an honest party, just by hacking the computer. So general MPC protocols with strong security guarantees against remote attacks is what I'm talking about now. We think about the machine already having received input. So you don't need to be online to receive your input. We think about the input already being inside of the machine. Now, we think about a remote attack now the machine is corrupted, and we would like to achieve by a clever protocol that the adversary does not learn the input or the output of the corrupted party, even though it is corrupted by a remote attack. And furthermore, the adversary is not able to modify the input or the output of the corrupted machine, unless all parties are corrupted. We cannot guarantee anything if all parties are corrupted. Okay. General MPC protocols with strong security guarantees against remote attacks. The protocols I will be presenting will be in the UC framework, so they will be working together, so you can compose them, that you can run them concurrently with arbitrary other protocols. And we will revisit the corruption model of the UC framework. Not captured so far is that a party might be temporarily isolated and therefore not remotely hackable. We will use this extensively. We will look at certain parts of the machine being isolated, and then, even though the attacker wants to corrupt this isolated machine, the attacker will not be able to do so unless the machine gets online again. We will isolate machines, for example, by air gap switches. Think of drawbridges. So you can get offline, then you're not hackable unless you are hacked already. And you can get online, then you can be hacked, unfortunately. We will look at data diodes, meaning P1 can send information to P2. All information sent from P2 to P1 is blocked. So P2 or an attacker on the channel cannot hack P1 because the attacker cannot even send messages to P1. So P1 is isolated, even though P1 can send messages. We will use some more very simple, remotely unhackable hardware modules, like our encryption module should be unhackable. Otherwise, we cannot encrypt and all our secrets will be gone. But this could be implemented as a fixed function circuit, need not be freely programmable, and could be thought of as being a very simple device, which is not remotely hackable. So our new framework, our variant of the UC framework, we call UC with fortified security. And we have two kinds of corruptions. The one is a physical attack. If the adversary is able to mount a physical attack, then he will gain complete control over the machine. And it's as in the standard UC model, the adversary will control the machine completely, and the adversary will be able to learn the inputs and modify the outputs. However, we are looking at online attacks, and online attacks cannot alter the hardware. So online attacks are a little bit less powerful than physical attacks, and we will give strong guarantees for such online attacks. So a physical attack is tampering with hardware, and remote attacks are not tampering with the hardware. So a remote attack is only possible if the machine is online, meaning able to receive messages. We assume that a completely isolated machine, not reachable by the adversary, cannot be corrupted by an online attack. Okay, recall what we would like to achieve. We would like to achieve that even if the adversary hacks the computer of the party PI, the adversary will not learn the input, will not learn the output, and will not be able to modify input or output unless all parties are corrupted. So let's have a look at the protocol. We have this complex PC, and we have an output interface module. I will explain this later. It's a very simple device. And we have the encryption module. We have a buffer. And we think that our encryption module and our output interface module, those are very simple devices which are not really programmable, which cannot be hacked. They are remotely unhackable. However, our complex PC and our buffer are remotely hackable. We're not able to protect such complex machines. Now, we have a sharing phase, secret sharing, but PI, the party PI, will be offline in this sharing phase. PI will be sending shares, which are then encrypted by the encryption module and stored in the buffer of PJ. PJ is offline and will later on collect what's in the buffer. So PI and PJ are either physically corrupted already, or they're unhackable in this situation, but still secret sharing is possible. We compute shares of the inputs and some other things. Then we send the encrypted shares, and we encrypt, we sign also the shares such that we have message authentication. Later on, I will tell you that we will be then afterwards deleting the signature key to make it impossible for the attacker to fake shares, even if PI will be later on corrupted. So after the sharing, we erase everything except for the shares we need ourselves, the decryption key, and the public keys of the other parties. In particular, we will erase the signature key, which we used to authenticate the shares. So because of this sharing, the adversary has to corrupt all parties to reconstruct the inputs. As we did delete our own inputs, there is nothing more to find for an attacker if the attacker later on corrupts us. We have only shares, and the shares are made in a way that you have to corrupt all parties to reconstruct the inputs. So this gives you an intuition why we can construct a situation that after the start of the protocol, after the sharing phase, even if online attacks happen, the adversary will not learn any input because everything is shared among all the parties, and the inputs and the shares sent away are deleted. Okay, then we start the online compute phase. Now we are online, we're hackable, and what we do first is that we will look at the shares we received in the buffer, and we will check the signature. And then if all the signatures are valid, we compute the desired function value, meaning we're not computing the original function, f, but we're computing the function on the shares, which gives you f on the original inputs. So we use a slightly different function to compute it on the shares and not on x, y, z directly. Okay, if all signatures are valid, we will compute the desired function in a distributed way, and now we want to give out an error if any signatures are wrong. Now we think about an online attack, and now we saw that the adversary doesn't learn anything because everything's shared before he can hack. But the adversary could still modify shares and try to modify results. So this would modify inputs, but we want to achieve that if the adversary tries to modify the shares, this will result in an error. Even a modification of the shares of the own input are not possible anymore because the signing key has been erased. You cannot like delay messages and try to replace them after you learned the signature key, because you never learned the signing key. So you cannot kind of go back in time and change the shares. So now I gave you an intuition why modifying the input will not be possible unless all parties are corrupted. And but there's one thing that's still problematic. One thing still problematic, that's your PC could lie to you. Even if the PC knows the result is 3, the PC could tell you, oh, the result is 5. And to prevent this, we need this output interface module. We would like to achieve that if the PC is corrupted and not trustworthy and lies about the output, then the output interface module will give us either a trustworthy output, which is the correct output, or an error. How do we do this? Okay. In the offline sharing phase, we give symmetric encryption keys to this output interface module and MAC keys. So the output interface module now gets from the party, which is offline, a MAC key and an encryption key. And instead of only distributing the shares of the input, we will also distribute shares of this symmetric encryption key and shares of the MAC key. And we will change the function to be computed that we will not compute the result in the clear, but we will, in a distributed way, compute the result in an encrypted way with this symmetric encryption key, which we gave to the output interface module. After we shared this key and the MAC key, we delete everything. So even if we don't know the key anymore, the key is shared and will be used in the computation to ensure that the result is encrypted and MAC'd. So the desired function value now is encrypted with the symmetric key, and MAC has a MAC tag and will be computed in a distributed way. And this encryption will be undone by the output interface module, and the MAC will be checked by the output interface module, because the output interface module is uncorruptible and knows those 2 keys. And so the PC cannot lie to us, because this will be checked by the output interface module. And so the adversary will only see encrypted function values, not learn the output, and will not be able to modify the output, because the MAC tag is not known to the adversary unless all parties are corrupted. So not learn the output, not modify the input. So as I said, the MAC tag and the encrypted function value is then handed to the output interface module. The MAC tag is verified. If it is okay, then it's decrypted and the correct result is given. Or an error occurs and your PC cannot lie to you. So the adversary has to corrupt all parties to learn the MAC, and then we will give no more guarantees if all parties are corrupted. And so a modification of the output is impossible too. Okay, if we implement it, there are some nice things because the remotely unhackable hardware modules have only to be trusted by their own owners. Yeah, I don't care about your modules. They don't have to be sent around like in this CUTS protocol, and they only have to be secure against remote attacks. So they don't even have to be tamper-proof because we don't protect against physical attacks with this protocol. So air-gap switches could be managed Ethernet switches. There are data diodes you can buy. And the encryption module could be realized by some hardware security module. You can buy such, and those are very well made, and you can think of those as being unhackable. And the output interface module is something you can maybe not buy, so you have to realize it maybe yourself or get some company to do it for you. You have to maybe extend a hardware security module or use an FPGA to realize it. But it's so simple that you can realize it without being freely programmable and being thus unhackable. Okay, coming back to when I started the talk, would it be possible that secure hardware makes all of MPC trivial? For example, trusted execution environments like Intel SGX, will it make all MPC trivial? Actually, it's a great promise that a trusted execution environment gives you isolation from the host system, gives you integrity and correctness of the computations below the operating system, and it's widely available. It's fast compared to distributed computations. And so the promise is that a trusted execution environment could give you security like a trusted third party, and you don't need distributed computations anymore. Just send all your secrets to the trusted execution environment, have it perform the computation and obtain the result. But it's not so easy. There are some vulnerabilities which can leak secrets. The algorithms on the SGX can be complex. So there might be errors there, and those could lead to exploits. The implementation is closed source, so we have to trust the vendor like Intel. And also, as an example, the SGX kind of talks to Intel in an undocumented way. Also, we might have to think about rollbacks. Is it possible to reset the protocol to a previous state and maybe try a new input, or is it protected against this? Also, it could be that the input-dependent timing gives you a side channel, because this is an algorithm you programmed and put on the SGX. It might be not side channel resistant. And so there are a lot of open problems, and there are many research questions. What is the appropriate model? What does the owner of the SGX learn? Is it kind of transparent for the owner? How could we have protocols not relying on full trust in this TEE? And how could we deal with these side channels or deal with these rollbacks or protocols dealing with input dependent timing side channels? So my summary is secure hardware yields everlasting security for MPC. I think this is really astonishing, and I would love to have this realized for high security applications where you kind of use all this quantum stuff. Secure hardware yields general MPC protocols with strong security guarantees against remote hacks. And both results are impossible without hardware assumptions. And replacing MPC by TEs in general, more research is needed, and I hope to make progress there. Thanks a lot.
Welcome back to the Crossing Conference 2021. We are going to continue with our pitch talks on emerging technologies. Of course, since it is emerging technology, we would also expect that the participants will kind of actively try to ask questions, but in virtual conferences, it's not always the same. So the first talk will be given by Lejla Batina. I would like to take a bit of time to introduce her because she is an asset of our community, and I remember that I met her for the first time at Eurocrypt in the time as I was young and beautiful and did crypto research. We met in Eurocrypt. Both of us were doing our PhDs, if I remember correctly. And since then, I am following closely what Lejla is doing in research, from side channel analysis to cryptographic hardware, but also applying new technologies or new ideas like machine learning to explore the side channel and power leakage analysis. She also is very active in the community with organizing very high-profile summer schools and conferences, like, for example, co-chairing Real-World Crypto Symposium, which is very popular event. Also a summer school in Croatia, which is a beautiful one and a very good one, a top one with a high number of participations, not because of the beautiful weather and the beach, but also because of the beautiful content. And I recommend you to register. I think next year it will be again in Croatia. Lejla is also very much busy with organizing Eurocrypt, which is a top crypto conference in Zagreb. And I assume that a number of participants in this conference will also join there. So register, and Go Zagreb is also a beautiful place. Anyway, so I think I have said just a bit of what Lejla has been doing in our community, and now the stage is yours.
Thank you. Let me just share my screen. Do you see my slides?
Yes.
Yes. Okay.
You have to full screen it.
Yeah, I'll do that now. Full screen. Okay. Okay, so thanks.
Great.
Thanks, Ahmad, for the nice introduction, and thanks for this invitation. It is a great pleasure. It would have been even greater to be there in person, but yeah, that's it for now. So let's do the best we can. Since Ahmad already mentioned, today is the last day of early bird for Eurocrypt, so you can still jump in and join the great program and the lineup there. Where, by the way, it's not just me who's organizing stuff. Ahmad has a workshop there together with Nele, who's speaking after me, with a great title, Sexy. So yeah, I'll leave it to you to Google it and still join. So I'm going to speak about side channel analysis and actually like where it could also lead one, basically to consider automated power analysis, evaluation, and elimination. And I will in particular introduce our leakage simulator called Rosita. So in terms of emerging, this is very recent work. And we also extended it now recently to Rosita++, but you'll hear more about it in the talk. It's a joint work from several groups around the globe. So from Adelaide, we have Yuvalia Rom and his student Madura, also Francesco from Switzerland joined, and from Radboud, my student Nils Samuel and me. So I'll try to go quickly over introduction because those things are mostly known, but nevertheless, it's important to reflect a bit to what we are discussing, because it also kind of gives a motivation to this work and kind of similar research efforts. So as you know, we have this known challenge with embedded devices, which all are kind of super important to be kept safe because we trust our lives, trust with those devices with our lives. So especially if you think of like pacemaker, as you can see on this picture, or like even things like self-driving cars, for example, that's not even so far future anymore. So there you really kind of trust that security is done well in terms of protection and even privacy, because it can result in the lack of safety in many cases. So known concern for those attacks are implementation attacks, as we know for decades now. So typically passive, like side channel attacks that exploit information that comes from physical signals like timing, power, and EM. But also fault injection falls into this category, but this is not in the scope of our talk today. And how relevant are those? Well, I just leave here two most recent pieces from the news, that there were several actually in between TPM fail and Google Titan attack. But these are kind of really attacks on chips that are used in the world, like these TPM fail targeted TPMs of Intel, NXP, and SD. And it was both in terms of root of trust as a hardware chip, or but also as a firmware running on a CPU. And the most recent one, this attack on Google Titan, that's also same CPU as in number of kind of smart cards that are used for IDs, for passports, and so on. So these are really like security products. And they were successfully attacks like in recent past with side channel attacks. So this really suggests that this challenge is far from being solved. So like, yeah, just a few more words. So we have typically this gray box or even white box scenario, depending on if you're considering just attacks in the wild. Those are where the adversary typically collects plain text ciphertext pairs, so similar as to black box crypto attacks. But then additionally, there are some information collected from signals like power consumption, line timing, and so on. So that's additional side channel information. And with white box, we can consider security evaluators. So people sitting in companies like Rescue, they do security evaluation of semiconductor products. And they typically get to know almost everything. And then they try all kinds of attacks that are out there. And depending on the outcome, they can certify chips up to a certain level. So this is kind of the background. And then we know even how to model the leakage. So when the attacks came out, so we first learned how to perform them in order to learn how to defend against them. So then typically the most commonly used leakage model is Hamming weight or distance, where you typically count the number of transitions from 0 to 1 or 1 to 0, and you kind of rely on the fact that knowing this, so will also make you in a way learn about data in some kind of remote way. You can imagine that this might work, considering that we can establish as the fact that power consumed will mostly depend on this so-called switching activity. So 0 bits turning into 1 and vice versa. And then of course countermeasures came. And there, the goal was actually to break this link. And one of the most well-known is masking, where because it's kind of hard to break this dependence of power of data, but then we don't maintain this link from the actual data. but rather data on which computation is done, which means that the actual data, so something that enters as input, should be in a way masked. That's kind of idea behind. And then we have it scheduled here. So typically we speak about Boolean masking as a sort of deep order in this slide, where we say that we ideally would like to split every bit of information into a number of shares. Here it's like D+1 to maintain D level of security, which means that even if the adversary learns up to D of those pieces, those bits, that's he or she cannot learn the secret V. And then this is kind of here simplifying for 2 shares, because that would be the first order security, or something that's kind of most desired. Let's say at the first level, you want first order security. And then the issue is that it's kind of clear that the adversary would need to learn both X1 and X2 to learn X, because otherwise the device remains protected. And then that brings us to leakage evaluation, which means basically when there is leakage, there is the need to evaluate. And again, this white box scenario like security evaluation lab, where we say, okay, if we protect in the certain way up to certain level of masking, then it should all work well. But that's just basically in theory, because in practice, there are all kinds of interactions that are not foreseen when you write the code. Think about glitching effects, where signals just propagate with a different delay and they don't arrive at the same time at the gate. Think about unwanted interactions between different storage elements in the chip. That's also something well known from the literature. If you, for example, store 2 masks, 2 pieces of one variable, like 2 masks in neighboring registers, then actually this Hamming distance could leak, and then you don't maintain the expected level of security. And TVLA, or test vector leakage assessment, is the well-known method to kind of evaluate this leakage. It's far from perfect. It only tells whether a device is leaky or not how exploitable the leakage is, even if you if you have evidence of it. But nevertheless, it's kind of at this first instance quite commonly used in evaluations. And that brings me to the main subject of this talk, which is leakage emulation and Rosita. So we kind of established the fact that leakage evaluation is necessary, and that doing that on a done product is quite often too late. Even if you don't consider ASIC like hardware chips, but something running on a microcontroller, that still could be, quite late if you make a product and then you realize, okay, it's too leaky. So people started looking into simulation, and that's where several simulators were proposed, most well known of those being Elmo, who's basically doing this emulation at an instruction level. So like typically you could emulate at the source code level, which is then platform independent, and it's nice because it's generic, but from the other hand, it doesn't give you all those microarchitectural interactions, doesn't model them properly. And if you go to the machine instruction level with a specific CPU in mind, that becomes then less generic, but kind of better model. And here you see some examples. So we picked up Elmo because it is well known and it's kind of really doing a good job, but for one specific CPU, so ARM Cortex M0. And that's how Rosita was born, say. So we have first extended Elmo, here you see on this slide, I will explain, to Elmo star by adding some more specifics into the Elmo modeling. And we added TVLA on top of that to evaluate the leakage. And there comes Rosita, which is basically code rewrite engine, which acts upon those TVLA discovered leakage points and fixes the code such that the new modified code is not leaky anymore. So that's the idea in the nutshell. And yeah, I will not also spend time on this. You can just look it up what Elmo is doing. So basically, it's been very tedious work of several months of this research group from Bristol, from Elizabeth Oswald. So they kind of template all the instructions and figured out several important things to identify this leakage that is then valid for this specific CPU, ARM Cortex M0. So we figured out after looking at where leakage appears that Elmo doesn't find all the things. So we extended with Elmo star with several things. Most important of those are to look at the combination of bits across the two operands. And basically, we looked at these pairs of instruction that interact via hidden storage. So that was a sort of problem. Those microarchitectural interactions are very hard to identify with just modeling instructions. So you really have to step in deeper and look at the way they interact with storage. And that brought us to this concept of dominating instructions. So here you can see in this code snippet that we check here if store instruction in step number 9 dominates EORs, so the bitwise XOR in step number 5. And if this is the case, one will notice leakage at line 9 where store takes place. And we did this for the whole spectrum. So all possible pairs of instructions were investigated in this way to kind of pin down exactly how these instructions are interacting. And you can see here that triangles actually points to the one that dominates, and circles is just interactions on the same storage. And this is how Rosita does. So just one simple example. So basically the voltage or the way power is modeled is a sort of regression. You see this formula taking some different variables into account and some coefficients. And then we notice at this load RB, where the storage from address R1 is equal to R1, we see some kind of unacceptably high leakage, which is caused by the leak from variable 2. Okay, but this happens on this instruction. And one simple fix, so this is now when you see the code, the way it works, one simple fix that Rosita does, it simply add instruction in between just before this load, because then you kind of separate those instructions further. And that also in a way is fixing these unwanted storage interactions, right? So this is kind of just sort of, no operation, but it immediately fixes the leakage that we had before. Remember, here was 10, now it's 0.014. So it's really just not rocket science, but it's really like basically stepping in the code and adding some small things in between, moving data, copying, pop instructions we also have. There are several examples in the paper, just to make sure that those two do not interact in an unwanted way. Okay, so this is the setup that we use. This is the discovery board with Cortex M0 and the oscilloscope. And these are the results on 3 different algorithms, crypto algorithms, so implementations that we were able to find both masked and for this specific platform that we needed. So these are all first order protected implementations. That's important, because the point here is that while on the one hand, in theory, secure, you have all these leakages. And this is what you get with AES implementation. So these lines going above those red lines suggest leakage. And same for Zudu and Chacha. And after
just a second, 5 minutes left.
Yes, but I'm there. No, no problem. Thanks. So these are fixed ciphers, fixed with Rosita, and there you can see that it's almost perfectly, all leakage points are gone, so it's taken care of, except for Chacha. So Chacha remained very stubborn on removing all the leaky points, and also it caused the biggest overhead of 61% with respect to Zudu and AES, which can be fixed with less than 30% overhead. Yeah, it's probably due to the fact that Chacha as an ARC cipher is also kind of does not lend itself well to masking as good as the other two, and that kind of remained the problem. So we even got the masked implementation of Bernhard Jung, who was presented at CHESS last year. So we would kind of expect this is state-of-the-art masked Chacha, but still it remained leaky. So this is the result of experiments with real hardware, with chips. So you can see how over 1 million traces there are no leaks with the fixed ciphers, that's the bottom part, and with non-fixed originals, say, we have here leakage clearly appearing after several hundred of K traces. So these are the results in terms of numbers. You see what it took, number of cycles for AES, Cha-Cha, and Zudu, original and fixed. And we were able to fix leakage points almost up to one single remain, but there were 200 in the beginning. So that really worked quite well. So the contribution was basically to come up with something that hopefully will come in for handy for not just security evaluators, but also for security developers, because we hope to provide this tool, this code rewrite engine that could fix, say, leak implementation for specific architecture. It remains architecture specific, but that's while on one hand limit, on the other, it's the benefit that you can really model properly all these microarchitectural interactions. So that's how we created Rosita. We showed that even millions of traces can be then shown to have absence of observable leakage, and the overhead is quite acceptable. So these are the references. I also said in the beginning, we extended recently Rosita to deal with higher order leakages as well. We use higher order evaluation tests like TVLA or higher order, and that's going to appear at CCS. So now you have a complete tool to fix your implementations for this platform, at least up to the, say, order 4, I think. Otherwise, it becomes too complex in terms of computation, but I guess that should meet the industry requirements. And I stop here. Thank you. Thank you for your attention.
The next honorable speaker is Nele Mentens. Let me also say something about Nele, because she is another asset in hardware-related community. She is very busy because she is now at KU Leuven and at Leiden University. So both universities want to have her. I mean, that's a great thing, but Nele is also great, and what she's doing is very exciting. So I met Nele as she was a postdoc, and I don't know what I was at that time, the first time in Leuven, as I had a research visit there. And I have been also continuously looking into her work, especially on configurable computing, which is currently very much in interest of myself as well. She is now working with plastics and security on plastics, which is actually very exciting topic. And she's going to talk about it, how far we can go. Nele, please.
Thanks, Ahmad. Let me first try to share my screen. So thanks again for the introduction. So the talk will indeed be on security on chips mounted on plastics. So I will say something about what we did up to now, because we started this research 2-3 years ago, and what we see as the remaining challenges. So first of all, I'll give a brief introduction on what are flexible electronics on plastics. What's the technology? What does the technology look like? And then I will talk about 3 challenges that we see to have security or crypto in this technology. And I'll also say something about challenges that still remain besides these 3 challenges, and I'll draw some conclusions. So first of all, flexible electronics on plastics are actually widespread, already used in commercial applications, but mainly in flexible displays. And in these displays, millions of thin film transistors can be integrated to control the pixels in the displays. So here the technology is already, or has been already used for many, many years. And it's only been like 5 years ago, 5 to 10 years ago, that researchers started to see also the potential of using the technology to build digital circuits. So not only displays, but real circuits that really have like functionality besides just being a display. And yeah, so there's many applications that can be made in this technology, like flexible labels, for example, on bottles or on packages, smart blisters, medical patches, etc. And it has already been shown that RFID or NFC chips can be made and can be integrated in paper or in plastics with this technology. And yeah, a few examples that have been published in this field are like an NFC chip and also a very small microprocessor with a limited instruction set. So there has, I mean, it's an active area of research to also build circuits in this technology. So what is the benefit of using the technology? So in this table, I tried to summarize that, and I concentrated, or I took as an example the AIRBUS technology, which has like 5 micrometer transistor gates compared to, for example, 10 nanometer technology in silicon. So these are some ballpark numbers. So first thing that you can see is that, so I'll start with the negative things to end with the positive things, the advantages. So first thing that you can see is that supply voltages is a lot larger, or we need a lot higher supply voltage in this technology, which also leads to a higher power consumption, which is not good, of course. Then also the charge carrier mobility is a lot lower, which means that the electrons and holes that are moving through the circuit, let's say when an electric field is applied, that the speed of electrons and holes is a lot lower, which leads to lower performance. Then if you look at transistor density, you can already see it, like 5 micrometer gates. Of course, for the same functionality, you need a larger area than on the chip. Also semiconductor types, like in this technology, we only have N-type transistors, which is then like unipolar logic, which typically leads to lower reliability of the chip, which is also a disadvantage. And which also causes like the effect that you can integrate less transistors in one chip, actually, if you want a reliable circuit. So, but then why would you use this technology when all these disadvantages are there? Well, for some applications, performance is not that important. For some applications, it doesn't really matter if the area is a bit larger, if we cannot integrate that many transistors, etc. But for those applications, it might be important that the cost is very low. So, and that is one of the advantages of this technology. If you look at the cost per 1,000 transistors, then the ballpark numbers are shown here. And you can see like a factor of almost 10, let's say, if I exaggerate a bit, or even over 10, I'm sorry, even over 10. So the cost is a lot lower, and this has to do with the fabrication process that can be run at a much lower temperature than traditional silicon chips, where you might need like up to 1,000 degrees Celsius for silicon chips. In this technology, it might be like room temperature up to maybe 350 degrees Celsius, which makes a huge difference. And of course, the chips are also flexible, bendable, stretchable, etc. So these are the main advantages. And for all applications where these advantages are more important than the disadvantages listed here on the slide, we can use this technology. So that's for making circuits in the technology. Another thing that we need if we want like chips that we can use for like real world applications, we also need non-volatile memory. There's also a big difference here with silicon chips where you can have, for example, flash memory. That doesn't exist here. So the only thing we have here is like one-time programmable storage mechanisms that are non-volatile, and that can be based on 2 methods. Additive method or modificative method. If we look at the additive method, very simple. For example, if we want to have like a cryptographic key, then every key bit that we want to program in the chip, we need to connect to a digital 0 and a digital 1, which is the ground and the power supply. And we need to put something in between, this interdigitated finger structure, where we can, for example, use ink to either connect the key bit to 1 or to connect the key bit to 0. Another method is a modificative method where we connect each key bit to both power supply and ground. And before turning on the power supply, we cut one of these wires with a laser such that when we turn on the power supply, the key bit is either programmed to 1 or to 0. And as you can see, both these methods are like one-time programmable. So once you can choose what the cryptographic key, for example, is. So we know now that we can make digital circuits in this technology. We know what the advantages are and also what the disadvantages are. So we can think of like which applications could benefit from the technology. We also know that we don't have like flash memory, although technology researchers are working on that, but it doesn't exist yet. We can do one-time programming actually if we want non-volatile memory. So the question is now, what are the security challenges? Because if you think of like an NFC tag, of course, we want to make it possible that, for example, a reader that passes by can authenticate itself to the tag to be able to read out data from the tag, for example. So what do we need for that? First of all, we assume that the tag is passive. So that means that the reader wirelessly powers the tag and that there can be data exchanged between the reader and the tag in both directions. So the first challenge that we tackled already, and yeah, okay, we're exploring it further, of course, is to integrate crypto cores in the flexible tag or the flexible chip. And the challenge here was that the number of transistors that has been reported in digital circuits, that had been reported before we started this research, number of transistors was much lower than the number of transistors that we needed in a crypto core. So that was something we had to explore, like was this possible or not? Second challenge was how can we prevent the key bits from being read out? Because if you remember, like the one-time programming method with the ink or with the laser cutting, of course, when you look at the chip, the features are very large, chips are not packaged, you can easily read out and you can easily see almost with the bare eye or with a very cheap microscope, you can see which key bits are 1 and which key bits are 0, because we don't have electrically readable writable memory. So that's the second challenge, which is specifically important for crypto circuits where a secret key has to be stored. And then the third challenge, we want to enable one-way or even mutual authentication. The challenge there is that the delay of an authentication protocol is typically too high to be within the acceptable delay for example, NFC or RFID communication. And another challenge there is if we want to have this kind of authentication, even if it's one-way authentication of the reader, then the tag needs to generate a nonce. So we need something that can generate a nonce on the tag. So these first two challenges we tackled at least partially in our chess paper 2 years ago. So I will briefly say something about that. And then the third challenge we are working on now, and our chip will very soon be fabricated such that we can also report on these results. So the first challenge was to have like a crypto circuit or a crypto core on the chip. We successfully managed to do that by choosing like a very, very small crypto core, which was Cadentan 32. And we managed to implement that in this technology with an 80-bit key. Of course, the security level is quite low for this algorithm. But yeah, it was a first start to see if we could at least do something. And then, yeah, of course, we made a measurement setup where the chip was still on the glass carrier on which it was fabricated. Of course, afterwards, if it would really be used, it would have to be taken off the glass carrier. But we did our measurements on the glass carrier using an FPGA and some level shifters to apply the right voltages, etc. And then we got these measurement results. So we fixed the key. Remember, we had this one-time programmable key or one-time programmable memory or method to have like a non-volatile key. We applied 1000 plain text and checked for the 1000 ciphertext. And then we saw that for power supply voltages of around 10 volts, and then some extra voltage that I didn't explain, the bias voltage of 15 volts, we got the correct ciphertext out at a relatively low clock frequency of 10 kilohertz, which led us to like a total latency to go from plain text to ciphertext of almost 32 milliseconds, which is very, very high if you compare to a simple chip. But as I said, for applications where this doesn't matter, we can use this technology. So that worked. And of course, we had to do the key programming. This is a real microscope picture of our chip. On the bottom, you can see part of the digital logic that was implemented. And on the top, you can see some of the key bits, actually key bit 26 to 36, where you can see that we used the laser method. So we connected each key bit to both the ground and the power supply. And then before turning the chip on, we cut one of those two wires. And if you zoom in, for example, on these two, then you can easily see that this wire has been cut on the left side and the wire on the right side has also been cut, which means that the key bit on the left is connected to the power supply and the key bit on the right is connected to the ground, which means that the left key bit is 1 and the right key bit is 0. So you can easily read out the key bits with a microscope. Like I said, the chips are not packaged, so you can very, very easily do this. And that's a problem, of course. Yeah, on a silicon chip, you can also do things to read out the memory if it's not properly protected, but at least that's a lot harder than in these chips. So we really need to do something. So what can we do? Because we know we don't have flash memory, for example. What can we do? The concept that we proposed uses lasering again, but not to cut wires, but to change the operating mode of the transistor. So what you can see here is on the y-axis, the current that flows through a transistor, and on the x-axis, the voltage that is applied at the input of the transistor. Now, starting from a certain threshold voltage, the transistor starts to conduct. And using a laser, what we can do is to shift this threshold voltage. And by shifting this threshold voltage, if we apply a fixed voltage at the input of the gate of the transistor, we can switch it from off to on or from on to, we can switch it from off to on for the same negative input voltage. And this is what we used, and we use it in this way. So we had like the transistor or the switch that we had on the previous page, and we used that to connect each key bit to the power supply and the ground. And then, so it would look like this. We have this negative voltage that we applied to each of these two transistors. And then by using a laser, what we could do is we would switch one of these two from off to on, such that the key bit would be connected in this case to 0. And if we do that for the top one, the key bit will be connected to 1. Yeah, so then we experimentally validated this. And yeah, we were a bit disappointed because what we saw was that there was a clear difference under the microscope between a lasered transistor and a not lasered transistor. So this is one transistor where you can really see like these edges here show that we use the laser to on this transistor. So the difference is visible between a transistor that has been lasered and one that has not been lasered. So then we thought of a solution. And the solution was to apply different settings of the laser to cause different threshold voltage shifts that you cannot distinguish easily. So we tried actually a lot of settings, and we found that, for example, these two settings would be good. And if I zoom in on these, then what you can see is that for the top setting of the laser, I'm not going to read it, but it's on the slide. You can see that you get the effect that we want, and that you can really turn the transistor on by lasering it. And for the bottom settings of the laser, you're setting 2. We would also laser the transistor with these settings, but the transistor would not be turned on.
Just a second, 5 minutes left.
Yeah, thanks. And if you look at the picture, then you can see that yeah, it's not that easy anymore to distinguish between the two. I'm not saying that if you like apply, I don't know, machine learning or some technique to really distinguish that it would not be possible, but at least it's not visible anymore by just looking. Okay, so that was challenge 2. We found a solution for that. Other solutions might also be to use ink to cover the places where we program the key bits. But then, of course, this ink should not make the whole thing conductive. The ink should not be transparent. It should not be soluble. So that's something that we are still exploring. And then for the third challenge, which is to provide reader authentication. A simple protocol for reader authentication would be that the tag generates a nonce, that, for example, the reader computes a MAC on this nonce with a pre-shared cryptographic key K, and then the tag checks if the MAC that was calculated by the reader is correct to authenticate the reader. What do we need for that? We need, of course, a digital crypto circuit, which we already have, because that's what I explained in the first challenge. We need secure key storage. That's what I explained in the second challenge. And of course, we need the nonce generator. Now, to create a nonce, we either need a true random number generator, or we need to have like non-volatile storage, because we need to know that the number that we produce will only be generated once. So we need to keep track of what was generated before. For that, we need non-volatile storage, or we need to know that it's truly random. And for that, we need a true random number generator. Now, there's some things that we need to explore. And this pseudo-CMOS is the technique that we use because we only have N-type transistors in this technology, and we need to explore like which effect this has on true random number generators. So, but like I said, this test chip will soon be fabricated, and then we can do the measurements to see what the effect is. So there's other remaining challenges. We want to look at puffs on plastic substrates, because of course the puff still needs to be reliable even when the chip is bended or stretched, which seems to be easier on a silicon chip that is not flexible. If we want to have mutual authentication between reader and tag, this would cause an even longer delay, which might be a problem. So that's also something to investigate. And maybe we need public key algorithms, but that would then require even more transistors. So that's something to check in the future. So conclusion, the technology is rapidly improving and soon also ready for mainstream applications. So we really need to look at security of these applications and of the chips that we build. And a number of challenges have already been tackled, but there's many more security challenges to be considered. So yeah, I think there's much more to investigate and much more results to be expected. Thanks.
So Stjepan is our rising star. He is doing, I would say, some kind of unconventional research, like, okay, meanwhile it is becoming conventional, but using machine learning in combination for, information leakage. And what is interesting, and he's going to talk about it today, is how deep can you go when you talk about deep learning. And indeed, deep learning is a hype, and we love it because all of them, from the security point of view, they can help us. And on the other hand, we can also attack them. So if the machine learning or deep learning helps you to get better leakage or analyze leakage, how do you take care of the deep learning itself? That will be the next problem. You're going to talk about it in the next crossing. Okay, Stjepan, thanks a lot for accepting our invitation, although I know that you are busy with changing between two universities. Please, the stage is yours.
Mm-hmm. Thank you. Okay. So just to check, you can hear me and you can see the screen.
Everything.
Excellent. So great. So thank you, Ahmad, for invitation. And yeah, today I will talk about deep learning based side channel analysis. How deep should we go? Basically, this talk will be different from many of my other talks, because in most of my talks on deep learning, on side channel analysis, I talk how deep learning is great, how we can break targets, how it's amazing. And while this is still kind of true, I want to talk about challenges. So I will talk about all those things that we actually do not know how to do well, or we are currently missing. That's why the title is also how deep should we go, because it asks the question, on what part of deep learning should we actually invest more effort, and what kind of deep learning do we actually even need to do? So when we talk about deep learning side channel analysis, we talk about profiling side channel analysis. And profiling side channel analysis have a prominent place as the most powerful among side channel attacks. Why? Well, because the attack model is assuming the attacker to be more powerful, to have access to a clone device of the device you want to attack. That's why these kinds of attacks are also called two-stage attacks, because they happen in two stages. In first stage, you learn about the target with your clone device, and then in the second phase, second stage, you really use that knowledge to break the target. And already from this, you can kind of see there is a lot of connection between profiling attacks and supervised machine learning. So what we would call training would come to a profiling. What we would call testing in machine learning would actually be the attack. And actually, people did realize that, and they started doing machine learning based side channel analysis. And here on this slide, you can actually see a figure how it looks like. So this figure is a bit more complicated than we need, but it's fine. So what we have a device. We know about the key from that device. We use the information about the key, about everything. We build a model. And how do we build a model? Well, in the, let's call it traditional machine learning models were all from random forest models, from support vector machines. Well, now with deep learning, models are neural networks. Once we build a network that performs well, we kind of assume there is a part of a data set of our device that we do not know the key anymore, and then we try to guess the key on that side. Of course, we can also be more realistic, and instead of pretending that we do not know part of the key, we can really do the attack on the different device, which will be commonly called portability. So this would be a general setup. And how did it all go? Well, profile attacks in the machine learning context started, let's say, 10 years ago, even a bit more, where, like I said, people used various techniques. And what is important, all those techniques gave good results, but more or less comparative with results that we had with classical profiling attacks like template attack that was now proposed almost 20 years ago. And the technique were also very similar. So with machine learning, you still needed to do feature engineering, and then you basically just built a model in a bit different way. Of course, what was the advantage of machine learning was that we could also do other things. So we could also pre-process the data, we could also do feature engineering, and so on. And then 5 years ago, 2016, people started using deep learning. Where, well, 5 years is a little bit maybe not precise, because many papers use neural networks more than 5 years ago. But it's not clear whether some of those papers actually did deep learning, because in that phase, we still kind of often forgot to write the number of layers in our neural networks, which would basically mean it's not clear, is it deep learning or is it shallow learning? But 2016, we had the first application of convolutional neural networks, and that started the new direction for side channel community. Why was it important? Well, because it worked great. So we managed to break targets. But what is even more important, we managed to break targets that are protected with various countermeasures, both hiding and masking, what Lejla was mentioning. But what is also great is that we did not need to do feature engineering. So remember, with simpler machine learning techniques, first you find the most important features, those features that are representative, and then mount attack on those. Here, with deep learning, we'll say, well, you're lazy. Let's leave everything to deep learning, and deep learning will find what is important. So that was the promise that people liked about deep learning in side channel attacks. And then if we talk about profiling attacks and machine learning, deep learning, we can divide everything into something like this. So the first phase is we have some oscilloscope or whatever, we do the measurements, and we obtain the raw data. From the raw data, next step would be data pre-processing. So after that, we will do feature engineering. After that, we would do machine learning algorithm selection and machine learning model training. And finally, we would do attack evaluation. So these steps, let's say, make the machine learning, deep learning flow. And now I will discuss a couple of challenges for each of the phases. And of course, to see how, let's say, lucrative domain deep learning side channel attacks are, here you can see some kind of setup for papers and data sets appearing in last couple of years. So as I said, 2016, we had the first paper on deep learning side channel attacks. And in that year, we had one. Already next year, we had 2, and then 7, then 28. Last year, we had 52. This year, we have 33, but that's the first half of the year. So we can see that the domain is quite active. Of course, maybe not as active as some other machine learning domain like security of AI, but this is actually extremely a lot of research done considering how to do deep learning side channel analysis. And what is important to mention is deep learning is very successful in breaking various targets, both symmetrically and publicly. And currently, what we use as deep learning models are rather small and very efficient models. By very efficient, meaning we need only a couple of attack traces to break the target. And then you can, from many papers, some of them mine, you can often see results like this. So for instance, template attack needing 10,000 traces or more and not even coming close to breaking the target. So guessing entropy tells you how many guesses before the correct one. While if you use deep learning techniques and things like that, order of magnitude and more or less traces to break the target. Or for public key crypto, you can see here yellow line, which would be the normal attack, and then going all the way to the green line, going to 100% on attack on public key crypto. So what we can say is there is a lot of success stories with deep learning for side channel analysis. And indeed, the domain sounds already well established and like many or most of the problems solved. But is it really like that? So when we talk about raw data, there are some important problems. So when we talk about data sets, and this is a very important problem because it connects to all the other phases. So most of the data sets that the community currently considers are software implementations with limited countermeasures. As such, they are relatively easy to break. And then you get a problem that we as the community say, well, the attacks are very successful, but at the same time, what we are attacking is very far from what would be really used in practice. And as such, the question remains, are the attacks really so good, or are we just attacking very simple things? And don't get me wrong, at the same time, even on those simpler things, other simpler machine learning techniques or template attack would be much less successful. So we did improve our state of the art. The question just remains, are we still close to just academic setting, or are we also getting closer to real world setting? Additional problem that we have is when we talk about proper, stronger countermeasures, we often assume the knowledge of shares, so the masks, for instance, in masking skills. But while the question can be how realistic is to have such a knowledge. Then when we talk about the second phase, about the data pre-processing, this is a very interesting phase because most of people prefer to forget about this phase. So do as little as possible on data pre-processing. So we actually do not even know how useful is pre-processing. There is a lot of papers saying, well, I did this, I did that, I improved the results, but there are no systematic works comparing various pre-processing techniques and seeing what is happening. What also a big problem is, already from 2017, we know that data augmentation, so making synthetic measurements to boost the performance of our models, is very useful. But still, even after 4 years later, we do not know what kind of data augmentation is the best to use. Should we use standard data augmentation techniques from any domain, or do we need specific data augmentation for side channel, and so on and so on. So this is one of the domains where I see a clear room for improvement, because most of people will simply forget about it and start later. While I have a feeling making the attack more successful makes sense to already start as soon as possible in our machine learning flowchart. So this would be one place to do. Next is feature engineering. And remember what I said about deep learning. Deep learning comes with a huge advantage that we do not need feature engineering. So we commonly, as the community, say we do not do feature engineering. But actually, this is not true. Looking at the most of works, they consider more or less the same data sets. And for those data sets, they commonly consider some predefined windows of features. So while we do not pick specific feature A, feature B, feature C, we select a window that contains a lot of features, but that is still not raw data. And then the question is that a good approach? Because more recent results showed that if we really use all the features, then the attack performance improves significantly. But at the same time, we get also much bigger neural networks that we require. So it's very much not clear, do we need feature engineering? And if we need, how to do it? Next, for algorithm selection, well, we as the domain, we are quite conservative. We use only a couple of different architectures. So most of our works are based on multi-layer perceptrons and convolutional neural networks. But even there, it's not clear what do we do, because connected with the first step, small data sets, not realistic data sets, it's very difficult to know how to select the best neural networks for our problem, especially if we would need to map to something that is more realistic. So it's very much not clear how do we select the best architectures. While we have a couple of papers that suggest methodologies, but those works are very specific, and they suggest that we basically need, for every small change in a data set, a specific architecture, which is something that most practitioners, security labs would not prefer. So labs would prefer to have a single or only a few architectures for all the data sets they can encounter, while we in the academia try to make as many as possible different models for many as possible different settings.
Just a second, 5 minutes left.
No problem, more than enough. Next, for the model training, what is big challenge up to now? Well, with deep learning, there is, of course, more hyperparameters than for simpler machine learning techniques. What we still do not know are what are the most important hyperparameters for deep learning side channel analysis. So there is a lot of papers saying, well, do kernel size that, do this number of filters, do this, do that. But actually, we are still a little bit confused what hyperparameters we should change, how to change it, and so on. What is also very important is that recently we started seeing works that suggest custom neural network elements. So for instance, custom types of layers, custom loss functions, and the results reported are very good. But it's still very difficult to know how to generalize those results for different settings. Because if we constantly just add new elements for specific settings, in general, this makes the situation more difficult because the next practitioner has only more selection to do. And finally, for the attack evaluation, we are still quite far from understanding the relationship between commonly used side channel metrics like guessing entropy, like success rate, and model learned parameters. So, for instance, the neural network weights, but also the how to estimate the attack performance, because once we are doing our training of our neural networks, we would measure the loss, we would measure the accuracy. But that loss in accuracy do not tell us how successful is the attack, side channel attack. And as such, we are in a problem that we actually often do not know even when to stop the training, or did we stop the training in the proper epoch. So this makes the attack evaluation rather complicated. But all that being said, all these challenges being said, of course, the results we are obtaining are indeed very good. But going for reality will require a lot more of our effort. So to conclude, in implementation attacks, machine learning, deep learning does seem to represent the most powerful option for side channel. What we see is that our state of the art in side channel is usually much simpler than in other domains. So in other domains, you will see deep neural networks with tens, more than 100 layers. Or for side channel, commonly you will see something up to 6, 7, 8 layers. So our networks are much smaller. And of course, while there are some specific parts we cannot transfer from one domain to other, there is also a lot of knowledge we can take from other domains, from image classification, from anything, and still apply to side channel analysis. What is important, of course, is at one point to not reinvent the wheel, but also what do new attacks teach us about improving the security of devices? Because in the end, we do our deep learning side channel analysis to assess the security of a device. But once we break it, this is fine. But the main question we should answer is, okay, the device is broken, how to improve the security? Unfortunately, deep learning does not give us much answers in that domain. It just tells us, yes, it's broken, but how to improve it, that's very much more difficult question to address. And with this, thanks for the attention, and I'm happy to answer questions.
In the interest of time, we go to our next honorable speaker that, as you see, these topics like justice and machine learning, automatic algorithms, but also aspects that regard COVID-19 and digital technologies are socially impactful topics. And this is why we put them together, because we have seen in the last 2 years the development of many digital technologies for helping to identify the infection chains and to classify them and try to kind of find out, so to say, to reduce the impact of the pandemic and COVID-19. But these technologies can also be used in more broader context and future. And we have seen that big companies, big IT companies like Apple and Google are trying to dominate here. And there are many governments who are running behind these companies without really thinking and without really considering the risks. And whenever researchers like the next speakers, Serge Vaudenay, start to criticize and start to look into the details of these schemes, and other researchers follow. And we also in my group and also in Crossing, we have done a lot of research in this area, and we had a voice of science to warn other scientists and other politicians not to fall into this trap of big giant companies dominate our technology and also our privacy, I would say. This is why we invited 2 big names here. One is a rising star, Joel, and one is already a big star, that is Serge Vaudenay, who has contributed to our cryptographic community for many, many years. But also the interesting things about Serge is that he's also looking into the practical side and bring it with the formalism together so that you can have more fundamental results rather than just arguing about the security of things. I remember on his modeling in RFID era, and also many other aspects. And Serge is also looking into security and privacy of as I mentioned, digital technologies in our pandemic era. And now he's going to talk about security and privacy compromises, although I know that he didn't have much time, but he accepted our invitation, and I'm very happy that he's here. Serge, the stage is yours.
Okay, thank you very much. Can you hear me?
Yes.
Yes, okay. So thank you very much for your invitation. So I'm sorry I could not join in Darmstadt. I would have been happy to be there, but I couldn't because of my course, and unfortunately I have to teach in the class, so I have to be here in Switzerland. So let's share my slide if I can. So thank you very much for your invitation. So this talk is about how people dealt with security and privacy for application related to pandemic and to fight the pandemic. And it's mostly about our curse. So you know that we have been cursed and we had been suffering for many things. And every time we try something, we try to deploy some new technology to try to fix the problems, and we had more problems. And it's essentially about this curse. So I will mostly talk about digital contact tracing and the one which was deployed based on Bluetooth. And then I will talk briefly about other technology which have been deployed too. About digital contact tracing, so the idea is that we want to be able to, so you have people meeting at random, and if someone gets sick, we want to be able to contact. So Alice here is getting sick. We want to be able to contact Bob in the middle, who has been in contact with Alice. That's the purpose. In contact means that they have been in proximity less than 1.5 meters during enough time, say 15 minutes. It's an arbitrary threshold which was defined. So that was the goal, and for that, people who deployed these technologies, they wanted to rely on technology, on hardware which was already deployed and available. So they used smartphones and Bluetooth technology, which is on a smartphone. So the idea is that a smartphone will use Bluetooth to send some random numbers, and it will work in silence. So now we have those people who are meeting at random, and every time of the day, so they carry their smartphone, and their smartphone is sending some random numbers over Bluetooth like a beacon. And this random number is changing from time to time. And their smartphones are keeping track of all the random numbers they have sent as a beacon and all the random numbers they have observed by scanning Bluetooth. So now Alice is broadcasting this number 3819, and eventually if she gets sick, she will get back some access code, and this access code will allow her to go to a bulletin board and to post all the codes that she has been broadcasting in the recent past. And people who watch at the bulletin board, or actually their smartphone, they will see those codes and compare with the code that they receive. And now we can see that Bob can see a match between the code on the bulletin board and the code that he has received in the past, and it will raise an alert. And for Charlie, it won't raise any alert because he has not seen this number before. So the principle is very simple, and it was deployed. It was deployed very quickly. It was developed in a few months and deployed very quickly. However, at the very beginning, many problems were already known, and they were not fixed at all. So it was known at the beginning that the precision of the Bluetooth measurement would be a problem. It was known that there would be some problem to have access to the Bluetooth interface because there are restrictions in smartphones to use Bluetooth. The adoption by people also, it was known to be a problem. So at the beginning, they say we would need something like at least 70% of acceptance, and we never reached 70%. Also, the epidemiological effectiveness of this technology was not studied at all, and it was an open question whether it would be effective. Of course, the security and privacy problems related to this technology were obvious, but they were not really fixed. And there are also some ethical problems which were not really addressed at the beginning. Okay, so what are the security and privacy issues related to this technology? So first of all, you have users wearing beacons, essentially. Their phone behaves like beacons. It's as if they were wearing a beacon on the top of their head. And so if you see in the street someone wearing a beacon, it's not very discreet. So the consequence is that you can discover all the users using this technology. You can see who is using, who is not using by just scanning. So I'm talking here about the technology which is called GAN, Google and Apple Exposure Notification. So you can see who is using it, and you can follow them. So if you have some network of sensor, a dense network of sensor which is deployed, you can follow people who are beaming some random numbers many times. You can follow them until the number change, and you can see when it changed, and you can see that it's replaced by another random number, and you can continue to track those people if you have a dense sensor network. You can also imagine that some malicious processes in a smartphone would be able to gather all the information that they send and they receive, so that they will be able to track people, essentially. So this is obvious. There are some applications like this application Corona Detective, which were posted on the web, where essentially the idea is to have an application which simulates, which works like the real application. It works exactly the same, except that every time it collects some data over Bluetooth, it also collects as much data as possible, like, for instance, the time of the day, the location of the day. It connects also with what we are doing. You can also enter some notes if you meet people, so you can say who you have met. And this application will remember exactly who gave the number which were received by Bluetooth. And if you see next some number posted on the bulletin board, you can connect with this application with someone that you have met, and you can say exactly who raised an alert on your phone. So who gave you COVID? So that's the title of this application. So you can have this type of application, which is a bit worrying. You can have attacks like it's an attack that I imagined in April last year. It's a paparazzi attack where someone would like to see if some celebrities get COVID and are diagnosed and report on the bulletin board. The idea of the attack is that those kind of paparazzi will try to capture a number sent by those celebrities. They are sent over Bluetooth, so you don't need to be too close to capture it. It can be done from far away. Once you have collected the numbers sent by their smartphone, you just have to wait and watch the bulletin board and see if this number eventually appears. Like this, paparazzi can track celebrities. People can also track their neighbors, their colleagues, their customers, their visitors. You can essentially see if they got COVID after you succeeded to capture one of their beacon number. There are also some other attacks. So I mentioned the problem of dense sensor network, which can be used to track all the GAN users. everyone who is using this technology. If you don't have a dense network of sensors, if you have a very sparse network of sensors, you can still do an attack, but not against all the users, but against all those who will get COVID, essentially. So here, that's a picture which was taken by a paper from our host in Darmstadt. So it's a picture from Darmstadt where you imagine that you have placed a few sensors somewhere in the city, and these sensors have captured some numbers, and those numbers were later reported on the bulletin board, and you can identify the movement of people who got sick this way. So it was written in the paper which was published here. So you have also these privacy problems. And about security, the problem of security is that now we can try to inject some false alerts on people's phone. And that's a security problem. You can imagine the lazy student attack, where a lazy student who didn't work enough would like to have a course cancelled or an exam cancelled, and he would like to inject some false alerts in the entire classroom or on his teacher or both. And like this, the exam would be cancelled. So you can also imagine some other scenario for this attack where you try to eliminate a competitor. It can be a competitor in whatever sense. It can be a sport competition. It can be some business competition. The idea is to raise some false alert on the phone on your competitor. Maybe you won't get rid of your competitor, but at least you will be able to stress your competitor and get some advantage, because this competitor will be under stress after receiving a notification. You can imagine also some kind of terrorist attack where we would massively spread some false alerts in a very wide population. Like, for instance, in public transport, we can spread false alerts in the entire train or in the entire area in a city. We can also imagine spreading alerts in the entire building in a company to make a company run out of business, to make a company close down. You can also try to do the attack on your own phone just to have a good excuse to escape from some boring events. Like, for instance, if you want to escape dinners at the in-laws, you can inject a false alert on your own phone and say, sorry, I have to stay away. Please have fun. And that's another attack scenario. So how can we do this type of attack? So these are the motivation for the attack, but how can we do this attack? So what was imagined at the very beginning is that someone could try to relay the code of people who will get sick. So in order to collect numbers of people who will get sick, you can try to collect them at emergency room, where people are sick and go there before they are tested, and after they are tested, maybe they are positive and they will report. So like this, you can have a guarantee to collect some numbers which will be reported with higher probability. And once you collect them, you can send them to someone else who will spread it to their victim. So it's a relay attack. You can imagine some more elaborate and more organized attack, like some kind of black market of numbers which will inject some false alerts. Here, that's an attack which was described in a paper written presented at ACNS 2021, where you have someone malicious who got sick and who has got an access code, and he wants to make money with this access code, so he can sell it on a smart contract. So you can say, I received this access code which allows me to post my numbers on a bulletin board, and someone malicious will buy this access code and will be able to post all the numbers that he has sent to his victim so that he will be able to inject some false alerts. You can also imagine many other cases where which are controlled by a smart contract. Here, the seller and the buyer do not even need to know each other. It can be done totally securely on a black market. There are some other attacks. One attack that I like very much is keep it simple, stupid attack. In the keep it simple, stupid attack, it doesn't work in every country. It works mostly in countries which didn't pay attention to this type of attack. It is an attack where someone gets sick and Alice gets sick and posts all the code that she has been sending in the past, including the very last number she has sent for instance, in the last hour. And if she is able to post the code that she has sent in the last hour, then it means that those numbers can be seen on the bulletin board and replayed immediately. So after 1 hour, the codes are still valid. So the adversary can see those codes, send it to a victim, and maybe the victim later will check the bulletin board and it will raise an alert. So that's the keep it simple, stupid attack. We have checked if this attack is possible by checking the bulletin board in many countries. And when we made the verification in April of this year, all the countries in red here, like for instance, Austria and Italy, this attack was possible. We could see some numbers which were posted and numbers which have been used in the very recent past and which were still usable. The attack in those red countries can contaminate also the orange countries, like for instance in Germany. If you see that on the Austrian server there is such a number which has just been used, you can try to replay it in Germany. And maybe later, these numbers which is on the Austrian bulletin board will be copied on the German bulletin board, and it will raise an alert to people to whom you have sent this code. So it's feasible in the orange countries. In the green countries, we didn't see such a problem, but the color of the country can change. Countries in gray also are countries we couldn't test, and countries in white are countries which do not use this technology. So that's one way to attack. Another way to attack is something we were inspired actually by some pretty old movies that maybe you know. Back to the Future. It's a movie from the 70s, 80s, I don't remember, where someone invented a time machine to travel through time. And one important rule for using this machine was never to set it to 2020. So we wonder why we couldn't set it to 2020. And now we have found the reason. It's because we could use it in 2020 to break this contact tracing system. So this is what we have shown at CTRSA on the effectiveness of time travel to inject COVID alerts. So here is how it works. Imagine that you have an adversary who can send his victim to any time in the past or future. So he can make his victim travel through time. Now someone is getting sick and posting some codes on a bulletin board. So the adversary can see when those codes were broadcasted by the sick person. And he can send his victim back to this time, replay this code, and then he just has to wait until the victim comes back to the present time, check the bulletin board, and it will raise an alert. So that's the attack. It needs a time machine. So far, we didn't succeed to make people travel through time, but to make a smartphone travel through time, it's very easy. There are several methods. First, you can have some physical access to the phone of the victim. And if you have physical access, you can just change the time on the phone. You can change the clock. If you can have some intrusion inside the phone, you can also change the clock, and it works. So like this, for instance, you can inject some false alert on yourself. If you don't have physical access, you can also make some rogue NTP server, assuming that the smartphone of the victim will try to check the clock value with the NTP connection on the Wi-Fi. This rogue server will intercept the NTP connection on the Wi-Fi and will essentially set the clock on the victim's phone very easily. If it doesn't work on Wi-Fi, and if the phone of the victim is setting the clock based on a network connection, you can also make some rogue base station. So this is one rogue base station that we could make. And it can be used to set the clock of the victim very easily. So for legal reasons, we couldn't test this in the wild, but we tested it in a Faraday cage, and it works very well. So you can change the clock of the victim's phone very easily with this kind of device. So the attack we imagine, so I won't run into the detail, but essentially within 1 second, we can make several jumps into time for the victim, and it would simulate an encounter of 15 minutes. So within 1 second, we can make the victim's phone believe that the victim has met during 15 minutes someone who got sick. It works very well. This time machine, we can also use it to break the privacy. So the idea is that if you have met someone in the past, we can try to see if this person, if the person that we are meeting in the present time was the same as the person we have met in the past. So for that, we can make this person travel back to the past and check if it is broadcasting the same number. We can also anticipate the recognition of someone we will meet in the future. And finally, we can also associate anyone to some unique number. So we can say, for instance, everyone we meet a person, we can make his phone travel in the future, 1st of January 2030, and see which number it broadcasts in 1st of January 2030. And if we do this systematically with all phones, we will be able to recognize all phones. Okay, so this is the attack that we made last year, and we reported this type of attack, and this is the kind of official reactions that we receive. Officials say that we are continuously monitoring the current development of the threat situation, etc., etc. And essentially, we don't see this attack as a problem, and we can live with it. So all those attacks, they exist, they are known, but nothing is done to try to prevent them. There are also some governance issues related to the development of this technology. So I mentioned that all those security and privacy, they were mostly known at the very beginning of the deployment. So in April 2020, I posted this report on ePrint where I have shown, for instance, the paparazzi attack and some replay attacks, which were possible. And essentially, it made no reaction from the developers. Actually, at this time, the developers were more pretty busy trying to eliminate their competitors because governments were adopting other technologies than the ones they were developing, and they were lobbying to eliminate their competitors. So what they did, for instance, is that they wrote these open academic letters that maybe some of you have signed, where essentially in these letters they say that governments are on the way to adopt some technology which is privacy intrusive, and it's not good. We have some other solution. Our solution is privacy preserving, and it's written actually in the letter that which technology is privacy preserving. It includes the technology by DP3T, which is the one which is deployed in Switzerland. So that was the problem at the very beginning. Instead of solving these security and privacy problems, they were busy trying to eliminate competitors. It was known also, so you may wonder why government changed their mind and switched to this technology. It's not because of this open letter, certainly not. It's more because of the problem of access to Bluetooth. Essentially, the access to the Bluetooth interface is controlled by Apple and Google in almost all smartphones. Apple and Google prohibit the use of a background of the use of Bluetooth in background. So on Android, this is the instruction that we can read. Launching silence Bluetooth scan without the knowledge of the user is not permitted by the system for privacy reasons, precisely. If you do so, your service might be killed in any moment without your permission. So it means that if we try to deploy this technology without the help of Apple and Google, it will be stopped by the operating system and it won't work. Or we have to bug the user all the time saying, do you consent to scan on Bluetooth? And it will be very inefficient and people will not use it. So this problem was known, and at the very beginning, there was a kind of alliance between Apple and Google and the developer of this technology. So the developers, they were trying to eliminate the competitors, and essentially Apple and Google said, we will help you, we won't help others, we will help you. And like this, they got fame and technology was deployed. But you know what happens when you make this kind of alliance? Immediately after that, it strikes back and you have some surprise. So the surprise is that instead of giving access to the Bluetooth technology, Apple and Google decided to implement the protocol. So actually what was left to develop in the app on a smartphone was almost nothing. So what was implemented in a phone by Apple and Google was everything which would select the random number, which would beam the random number, which will collect the random number, which will do the matching. What was left to be done by the app was to communicate with the bulletin board and to have the graphic interface with the user, and maybe also to choose the parameters for the risk evaluation in other way to say when to warn the user or not based on the number of encounters, based on how long we have met someone, etc. All the rest is done by Apple and Google. So so now we don't have much in the app. Nevertheless, there were some other problems, like for instance in Switzerland we have the parliament, the federal parliament has lots of power. And at some point, the parliament says that we want to have a legal basis for this technology before we deploy it. So for that, they changed a law, the law on epidemics. They added an article, Article 60A, in June 2020. And in this article, which is a bit long, but on alinea 5E, it says that the source code must be public for all components of the system. So it's a requirement by law. It's written by law, and it's actually written also in the joint statement by the DP3T developers that the source code of all components must be public. Of course, the source code of the GAN API is not open source, and then you have a problem. So it was known that there would be a problem. In this article, it's also said that in alinea 7 that the government is in charge of the details. So the problem of this API and the source code of this API is the details that the government was supposed to fix. So how was it fixed? Actually, so this law was changed on June 2020, and the application ordinance was published in June 24, 2020. So in June 24, 2020, 4 days later, the ordinance was published, and in Article 2, they define what is a component of the system. So here the law says all components must have a public source code. And the trick is that they decided to define what are the components. So normally everybody would understand what are the components, but apparently it requires some ordinance. And in the ordinance, they decided to do an exhaustive list of what are components. And of course, the GAN API is not a component. It doesn't appear on this exhaustive list of components. It's not a component, nevertheless, it's doing something. It appears in Article 5, Alinea 2, which says that the app, SwissCovid, can do some work with the help of an interface of the operating system. So this GAN appears as an interface of the operating system. This Alinea describes all what the app is supposed to do. And in the list of all the tasks of this app, almost everything is done by this interface of the operating system. It's not helping, it's just doing. It's outsourcing, it's not just some help. And to make things even more precise, in Article 5, Alinea 3, it says that the function of the operating system do not need a public source code. So problem is fixed. It's fixed by the governments. This is not subject to the law. It's escape from the law. So it's kind of bypassing the spirit of the law 4 days after publication. In Switzerland, we also have some other democratic protection against this kind of thing with the ability for people to submit a referendum. So there was a referendum against this law. Problem is that, strictly speaking, the law is very good. The problem is the ordinance, not the law. And so people trying to object to the law, but they didn't object because of SwissCovid, they objected for other reasons. So they objected, they say that the measures to fight against COVID were not proportional, say it was just a flu, they say that the governments and media are just scaring people. This was the argument to fight against the law on SwissCovid. It has, in my opinion, nothing to do. There are also some other weird arguments that I don't want to enter into some details. So this was the argument for the referendum, and the referendum failed, and the law was maintained. Okay, other problem solved. Another problem is that you have also some regulation for medical device, that's for health protection. So for all medical device, you need full transparency. Actually, the idea is that it requires the aware consent of people. People who would use this medical device needs to give their aware consent. For this, they need to be aware about everything, all the possible consequences, all the possible things which can happen, all what is published about it. For this, we need full transparency audit, and it's a very heavy process to get some approval for a medical device. SwissCovid is considered as a medical device because it gives some infection probabilities. It's considered as a medical device. There is no doubt about it. So it's subject to this regulation. In 1st of July 2020, an ordinance about this regulation was posted, which says that, okay, so if the evaluation of a new medical device is not fully done, we can still authorize if it is for public health reason. So this regulation is done by the government, and now the government is deploying some medical device like SwissCovid, and it is pain in the neck for everyone who wants to develop a medical device. It's a pain in the neck for the government too, so they find a way to try to bypass it. And they can bypass by making an ordinance saying that we can authorize if it is for public health reasons. Apparently, it was not enough because 1 year later, 1st of July 2021, they published another ordinance saying explicitly that SwissCovid is no longer subject to regulation. So next problem is fixed, so we can it can be deployed. Now, the next question that Ahmad mentioned is that we essentially have to live with many big companies like Google, Apple, even Amazon and Microsoft. So we mentioned the problem of Google and Apple, which are not considered as privacy models, at least for their reputation. So when we bug the experts or the developers or people responsible for the development of this technology, what they answer is that they say, but what Apple and Google implemented is what we recommended, so it's not a problem if it is them. So it's our technology. So this is how they try to make this technology adaptive. Also, it's deployed by Apple and Google, and some people are skeptical about their intention. The other problem is that, again, is not open source. So the annoyer, public annoyer is saying that all components must be open source. It's written in a law. It's also written in a public statement. But the expert says that GAN is not a component. It's just part of the phone. If it is part of the phone, it doesn't need to be open source, except that, for instance, in Android, GAN is not okay, it's part of the phone, but it's not part of the operating system. It's not part of the hardware. It's one kind of application which can be removed. And if you remove it, you still have an operating system. Your phone is working, and it's working very well. But you cannot use, for instance, Google apps. Another problem is, which was mentioned, is that the server is hosted by Amazon. So it is something which circulated, and the experts say, no, absolutely no. The servers are controlled by the federal administration. But that the public annoyer says that, okay, so my phone, which is running SwissCovid, it's making some connection to some IP address. And if on my computer I type host and this IP address, it says it is Amazon. So if the servers are controlled by the federal administration, why is Amazon displayed? And the experts say, oh, but it's not a server, it's a CDN. So if you wonder, if you have a problem when servers collect lots of data, and now it's just Amazon CDN which is collecting lots of data, it's considered as not a problem. So it's a problem if it is a server, but not if it is a CDN.
Just a second, 5 minutes left for the talk.
Okay, I will rush, thank you. Other problem is that the hotline is hosted by Microsoft. So now when you receive an alert, you're invited to fill up a survey. And this survey is actually filled on some Microsoft server, which is located in London. So it's not under GDPR jurisdiction, for instance. So the annoyer says that upon alert, we have to fill the survey on Microsoft, and the expert answer, okay, so it's not a problem because when we receive an alert, we warn the users that they're leaving the app. So if they continue and fill this survey, it's not our problem. So this is how it was solved. What is next? So we mentioned, okay, we'll skip this. We mentioned SwissCovid, but there is the good, the bad, and the ugly. So you have other technology like the social pass application and the COVID certificate application. The social pass was maybe some kind of app to do some backward contact tracing. So what I mentioned so far was for forward contact tracing. So here it's a network of infection when you have some red person infected some other. And you can see that if a person infects 2 or 0, then the probability that when you spot an infection, it prevents some spreading, it's 50%. And with a network with the same number of nodes, same number of edges, but you have people infecting 3 people or 0, then the probability goes down. And in the case of COVID, it's even worse than that. And it was known from the very beginning. And for that reason, the forward contact tracing is not so efficient. And we have to think about trying to not to see who we may have contaminated if we get sick, but who may have contaminated us and we could continue to contaminate others without even knowing. So that's the idea of backward contact tracing. And for that, you had these applications that probably you all know, where which was made mandatory in the state where I live when we go to restaurants or theaters or whatever, where essentially we have to scan a QR code at the entrance and at the exit. And if someone was sick inside this place, we receive a notification. In this application, Social Pass, which is mandatory in those places in the state where I live, this application is a proprietary app. We don't know what it's doing exactly, and it essentially collects everything, the IDs, time, location, etc. So for sure, there is no privacy. There is also the competition of a new version of Swiss COVID. It's called Swiss COVID 2, or the checking capabilities, where essentially when someone organizes a party, you can use Swiss COVID to ask people to scan a QR code. And if someone gets sick, the hospital will see that this person was at this event, and the hospital will contact the organizer and ask the organizer to post something on a bulletin board. And people, the app will be aware that something went wrong during this event. So for each entry on the bulletin board, it may correspond to 1 hour time at one location inside this event. We can try to monitor how much this was used. This is what I did. So for the Swiss COVID, I measure 2 entries in August 4, 13 in August 5, 8 in August 6, 4 in August 11, 1 in September 3, and that's it. So remember that each entry corresponds to 1 hour at one place in an event. So probably from August 4 to August 6, it could have been someone at a festival, like for instance, the movie festival in Locarno, the date coincides, who have been in many rooms, and all the entries are posted. So you can see that presumably it was used 3 times in the last few months. So it's not used so much. And the last application I wanted to mention is the immunity passport. So here, when someone gets a vaccine, at the same time, this person receives a certificate for having received a vaccine. And this certificate can be converted into a QR code. So when someone wants to control, you just scan the QR code. And this QR code is containing lots of information, like the identity of the person, what type of vaccine this person has received, when, and some other details. It's not privacy friendly, and in Switzerland, the officer for data protection asked for a lighter certificate. So now there is a scheme to convert this heavy certificate in some lighter certificate, which is valid only for 2 days, and which contain only the ID of the person and the fact that it is a valid certificate, and nothing more. So it doesn't give more information. So it leaks less data, but the consequence is that every time we need it, we need to send a full certificate to a central server. So now we have a centralized system which collects all the data, which is when we need a certificate, when we need to show certificate. So what happens with this immunity pass is that it's based on ID. So it means that every time we need to show certificate, we have to show an ID. Also, normally we should not have to show an ID all the time. It's based on a QR code. I've seen that some people try to do some denial of services attack with a QR code by injecting some error on the verifier's phone. This light certificate is also centralizing all the information about the certificate to a server, which is not good at all. And maybe it's even going through Amazon. So actually, this certificate is based on a PKI. So, and every time you try to have an update on this PKI, like the revocation list or whatever, we have to go through Amazon. And so Amazon can collect data. And finally, the ethical problem is that it is a discrimination tool. And this problem is not really considered. So to conclude this, I think we can just take it as privacy has gone. With all those techniques, there is nothing much to hope about it. We can wonder what did we get in return. I don't think it was so effective. maybe for the future, what we should do is, before doing some technological solutionism, we should really think about security, privacy, and ethical issues, and see what kind of trade-offs, and at least to be transparent on all those problems, because I don't think that we were so transparent about it. And finally, maybe a more positive note is that maybe it was nice that we had this, because it kept us busy, and instead of becoming crazy during lockdown, we could work on this. Now we can wonder, what did we get? So thank you very much for your attention.